Is Dr. Namandowski from like Ukraine or Russia? Yeah.
Hello, everyone. My name is Evgeny Glushkov. I'm the Vice President of the Executive Committee of the International Physicists Tournament. And we will start the live stream of the final of the IPT 2020 in 5-10 minutes. We're preparing it now. Thank you for your patience, and we'll see each other soon here. So apparently the participants cannot hear us.
Now it's okay.
It's okay?
Before I didn't hear, but now it's perfect. Maybe other participants and other team members can prove it.
So before we officially start, I will just mention that we have a special guest today that will give a short talk after the final and before we announce the results. It will be Bruce Yini. And if Bruce, maybe you can quickly introduce yourself so that the viewers know what to wait for all these 3 hours.
I'm not sure if I should say good morning or good evening or afternoon or whatever. But anyway, yeah, I'd like to thank you for welcoming me the way you have, and I look forward to just giving a short review of my life through education and my love for science, and how I eventually got hooked up with the IPT program. It's been fascinating watching the challenges here, and I'm very impressed.
I guess you shouldn't also be shy about yourself, and because you have done so many amazing experiments.
Well, I can, as I said, I'll try and explain a little bit of how I got to that point. And it really comes down to a view of how education should be taught. And I'll save those words for after the finals instead of.
Thanks. We really appreciate having you here with us, Bruce, because it's a great honor as well. We were watching your videos and getting inspired by your videos and adding the problems to the IPT list, and then IPT participants were also using you and your videos as a resource to prepare their presentations, their solutions as a base for them. So it's been a really nice collaboration in a way, which we hope will continue, because I'm pretty sure that our values and our approach to physics education are very similar.
I couldn't agree more.
Of course, we will post, for those of you who don't know about Bruce and his wonderful experiments, we'll post the link in the chat window to his YouTube channel if you get bored by our presentations.
Thank you. I appreciate it. It's been quite a journey. A year ago, I never would have expected to be sitting here presenting a short speech to the future of not just of science. Really, I've been impressed with watching the conversations and the battling back and forth, and it really does my heart good to see this. I'm, as I said, and this year, as troubling as it's been, it's really impressive to see this. So I'll stop there. I'll give my speech.
Thanks, Bruce. Just wanted to have a short introduction so that everyone knows what to expect. And now I think we are ready. We have
all the teams present.
Yeah.
Yes.
We have
all the jury members in the room. Yes. Okay. Shall we start? I've been told we have some problems on YouTube with some lagging. Should we start anyway? Evgeny, you are the master of
I
ceremonies.
think we can start, and then we will try to solve all the problems on the go.
Okay. So we can start. Welcome everybody to this 2020 final of the International Physicists Tournament. I'm very happy to see you here. I hope that this edition was not too much of a stress for all the participants, which had to go through so many difficulties to be here. We'll just spend a couple of words before leaving the scene to the three teams for the final. I just wanted to mention that this year was definitely hard. It was definitely hard for both for us, for the organizers, to put together this tournament from scratches. We had a lot of plans for this year. We were in the process of even being recognized as an official organization by the European Physical Society. We had so many plans in mind also to be able to offer to all the students some new opportunities for their academic careers and chances to gather together from all parts of the world and create a community and the experiences and memories to that bring with them for all their life, just like happened for us in our respective editions of the tournament. But of course, life doesn't always go according to plan, and we are incredibly happy to see that most of you didn't give up. You had a choice. You had the choice to just not be part of this tournament, just go on with whatever you were doing in your lives and forget about this edition. But you decided to take it the hard way and be here despite all what we were faced on, and especially as volunteers, and as this is not our main occupation, and see the motivation of students and people that seeing your love and your passion for these things is really what motivates us to be here, and is really what pays us back for all the sleepless nights we had in this week and all the hard moments and the kind of delusions for not being able. We normally meet only once a year, and this year we had to skip, and this was very sad, but at some point we were incredibly happy to see that the community is stronger than this, and that you decided to be part of it despite all. And we really want to thank you all for this. And this tournament, of course, would have not been possible without the most amazing team that I could have ever imagined of being part of. All the Execom actually put a lot of passion, a lot of time into it, and I'm very happy to have shared this year of hardship with them. Starting from our Vice President Evgeny, which will be the Master of Ceremonies for this final. Our current Secretary Vladimir, which is not present here, but is our had a lifelong service in the IPT, and is our reference for wisdom and advices on the tournament, and all the other members of the Execom, from Nikolai, David, Mateus, Alberto, Suzanne, and all the new members which recently joined and they are still trying to find their place within the Execom. And I really want to thank you all for being part of it and putting your time into this.
Of course, we have to thank Seba, our IPT president, who was moving the whole team forward during the last year, even if it was not easy. You were reminding us of deadlines and of important tasks, And this was a great journey to do together. So thanks a lot for that.
It was a weird experience for me because I was really one of those people attached to the physical gatherings. I was really one of which loved actually to meet people, and but it was really a surprise to discover this side of also for me, for these new sides for the tournament. We really hope to see you there next year and to make up for all the lacks of talks and gatherings and parties which we missed with this edition. Okay, before really becoming emotional, I don't want. We should probably start with the Anastasia, which will be the chair for this final.
Thank you, Sebastian. Thank you, Zhenya. It was really nice and warm words. Yes, my name is Anastasia. I'm a research fellow at University College London, UK. Yes, and I will chair today this final fight, and I welcome everyone. It's really great you passed it through all this stuff, through all these 3 selective fights. Shall I start with a bit of housekeeping? We suggest we have several people of the execom on the fight, so you can text either of us if you have any technical or organizational question, because actually when you unmute yourself and speak, it creates much more mess comparably to when you text us. Especially for jury members, we have here Nikolai Lutsenko. He's going to be responsible for gradings. So when you will give your grades for after each round, please text them privately to him. I think that's it. We shouldn't say anything else. I would like now to start introducing of the teams. Shall we start with Russian team from the first place? Can you introduce yourself? Unmute and introduce yourself.
So, do you hear me? Clear?
Hello.
And maybe now it's better?
Better.
Okay. So we're a Russian team. We can see, and our team consists of me. I am Ivan Polonik, Lena Zorygina, Ivan Kolesnikov.
Maybe some technical problems.
Yeah, we've lost you, yes. Shall you start from the beginning? Doesn't help. Hello.
Yeah, so do you hear?
Yes.
So we're Team Russia, and our team consists of me, Ivan Polonik, Lena Zorygina, Ivan Kolesnikov, Artem Sukhov, and Karnov German, and also Dmitry Spinov, who isn't with us.
Thank you. Let's move then to Ukrainian team.
Hello, we are a Ukrainian team. I'm a team captain. Grigory Ovcharenko. Here is Polina Kaufman, Darina Sherban, Semyon Kononenko, Oleg Ivashchenko, and Mikhail Gritsenko. Thank you.
Thank you as well. And finally, please, the US team, can you introduce yourself?
Hello, I'm Mateus Barbosa, captain of the US team. And my team members are Bob, Junzi Bao, actually, Kevin, Pung Kripawacha, and Carlos Ayush, and Carlos Marcia.
Great, thank you very much. Also, we have another important group of people in this fight is our jury members. I would like jury members to introduce themselves. Let's do this in the order as I see you. So let's start from Aki. Can you introduce yourself?
Yes, my name is Åke Andersson. I am a PhD student at the University of Gothenburg, and I've been with the IPT since 2015.
That's a great career, thank you. Now, Pierre-Louis, can you introduce yourself?
Good. So I'm
Hello.
Pierre-Louis de Assis. I'm a professor at Unicamp, the State University of Campinas in Brazil. And I work with quantum optics, integrated quantum optics.
Super, thank you. Now, Sonia, can you please introduce yourself for us?
Yes. Hi, everybody. I'm coming from Italy. I'm an astroparticle physicist, and then I moved to, I was working at CERN, and I'm also interested in science communication. I have a teaching experience, so I really enjoy to join this competition. And I wish all the teams really good luck for your future and this fight.
Thank you. It's really good wishes. Then Leandro, can you please introduce yourself?
Yes, I am Leandro Tessler. I am a professor of physics at Unicamp, the University of Campinas in Brazil. I work with amorphous semiconductors and rare earth doping, but this last semester I became a modelist for pandemics, and I'm trying to work with that.
That's an important role. It's very true. Also, I think I have Nikolai here as a member of jury, if I don't not mistaken. Oh no. Okay, if in this case I think we didn't forget anyone. We introduced everyone who takes part in this fight. Now we have to move to the Capitan fight. So this year Capitan fight gonna be run somehow separately. So we will have a set of questions for you. You will have to reply to them, and then our jury members will assess your replies according to how you get close to the correct answer. We have set of these tasks. Some of them will be theoretical, some of them will be experimental. I will try to do it in kind of fair order, so each question we will switch the order of replying to get a bit more practical. I think I can share now the screen with the presentation. I hope so.
So normally during the final, the captain's fight is the core activity. So captains, be prepared for some hard work.
Yeah, that's very true. Can you see my slides now?
No.
That's a pity. Okay. Maybe it takes some time.
Yeah, just wait a bit.
It says that you start demonstration, but we see nothing.
It may take some time, so let's wait a couple of seconds.
Yes. Can you see it now?
Yes, now.
Yes,
Yeah.
perfectly.
Super, that's great. So let's talk a bit with the rules. So again, the idea, we're gonna ask you several questions in a row, and after each question, we will listen to your answers, and then our jury members will grade your answers. We have the last more advanced kind of question, but for all other questions, you're gonna just give some number for us, and the jury will assess how it's close to the correct number. And we expect this assessment being in logarithmic scale. Yes, and again, if it's something where you can provide some error estimate, we expect that we consider that two results within the consider an error estimate given something close to each other going to be kind of equivalent. Do you have any questions about the Capitan fight? I'm asking the teams, also jury members may ask any question if you have. Looks like not, so let's go on. Question number one, you're gonna have 2 minutes. And here we are asking you to estimate something theoretical. Theoretical question number 1. So if you fly on the modern conventional jet airplane and you drop from the air some aluminum piece of fuselage and you fly at that moment over the deepest point of Moraine Trench at 11-kilometer height. So it's natural that this piece of fuselage will hit the water in 3 minutes. We calculated them, this stuff. So the question is how long it will this piece fall in the water until reaching the bottom of the ocean. You have for this 2 minutes. Your time started.
While the team captains are thinking about their estimations, the observers of this live stream on YouTube can also write their guesses in the chat, and then to the ones who guessed the best, we will also give some prizes.
You have 15 seconds left. I expect your estimation sent privately to me in the chat. Time is over. Okay, I've got reply from Russia and Ukraine. US team, I need to reply.
I'm trying to anesthesia, right? Okay, there we go.
Okay, thank you. So I've got 3 answers. Ukrainian team gave 3,000 minutes. Russian team gave 5 minutes. US team gave 1 minute. So that's the correct answer. I don't know it either, to be honest. Yes, the correct answer is 145 minutes. You can see the calculations here. So now our plan is, for member of jury, I would ask you to send your grades for this task directly to Nikolai. I can repeat for you the answer from the teams. Ukraine gave 3,000 minutes. Russian gave 5 minutes, and the US gave 1 minute. Nikolai, can you notice me when you receive your grades, please?
Yes, sure.
Super.
I would like to remind to our jury members that they have to send to me just 3 numbers, 0, 1, and 2. 0 would be for like lowest grade.
Lowest.
Yes, the 1 point, it would be the middle grade, and the 2, it's the highest grade. So like this. Mm-hmm. Mm-hmm. Yes, yes, you can point any team with any grade. So you can choose three the same grade. It's not obligatory to choose different grades.
Yeah, it's not exclusively like 2, 2, 2, 1, 1, 1.
Yeah, that could be. Mm-hmm. So I have received three grades from so 4 grades now. Do we have
Is it over now, right?
Yeah, do we have 4 jury members?
Yes, we have 4 jury members. Yes,
Great.
yes.
So
Super.
yes, I calculated the result. So we will reveal it later.
Okay, great. So now we can move to the second question. So you've got the point how we're gonna run our captain fight. I hope so. We got the point too. It's very informative. So theoretical question number 2 is about this huge ship. It's called Academic Lomonosov, and it is a new type of floating nuclear power station. And its displacement is 21,500 tons. The question is, you need to estimate it is 1.5 minutes, and you will given from 0 to 2 points. The question is, how populated a Russian town with average electricity consumption per capita may be powered by it? Your time is started. You have another 30 seconds. I've got your replies, thank you. So the replies are from Russian team, it's 100,000 people. For the US team is 41,350 people. And for Ukrainian team is 200,000 people. The correct estimation is the following. Is the following. So we can find out how much power is consumed per capita through some available data. We can find out, just estimate the amount of people in cities and how they consume the power. And it gives us enough information to estimate this number. So I'm typing the replies from the team to the chat for jury members, and we are waiting for your grades for the question too. Do you have a graders, Nikolai?
Yes, I have received 2 answers from Pierre and from Oke. And now from Leonardo. Leandro, sorry. Yeah. Yeah, I have received all the grades.
Super. We can move to the following task. Question number 3. It is about if you live in very remote area, but you still want to watch the IPT final. So suppose you are using a parabolic satellite antenna to increase the quality of your 4G LTE. We suppose it's band 3 with frequency 1,800 megahertz. And your purpose is to watch the IPT final from the remote place in good quality. And your question for 2 minutes, for which you can get from 0 to 2 points, is what maximal increase could you obtain in decibels if antenna diameter is 1 meter and focal distance is 60 centimeters? Your time started. You have another minute? Chinese reply from Russia and Ukraine. Okay, Russian. Okay. So I've got the replies from the US team 26 decibel, from Ukraine 10 decibel, from Russia 3 and 5 decibel. But the correct calculations are the following. So we consider that the receiver, whatever it is placed in the focal point. So using this, you can estimate the increase by this formula. And actually, you can assume the spot size and using this ratio and having the frequency value, you can get the value of the dB increase. So I'm typing the replies to the chat, and we would like the greatest to the greatest for the task 3.
Yes, I have received all the answers, all the grades from the juries. And it's interesting that all the juries sent me the same grades.
That's good. It verifies the legitimacy of our grading system. So we can move to question number 4. In question number 4, you asked it to estimate the teapot moment of inertia. So you have the picture of this teapot, and you need to estimate the moment of inertia of the given considered scene value teapot if it's rotated about its vertical symmetry axis and having its diameter value 40 centimeter. Consider that diameter is the largest distance between 2 points of the surface, and its total mass is 200 grams. You have 2 minutes. You can receive from 0 to 2 points. Your time is started. You have another minute. Russian team, I need your reply. Okay. Russian team made me math, providing results in grams and centimeters. Okay. So I can send you the answer from the team. The Ukrainian team provide answers 0.024 kilograms per meter squared. Russian 30,000 grams per centimeter squared, and the US team 0.013. I've sent it to the chat. I can now give you the correct answer. So our estimation gave us the value 0.0096 kilogram meter squared. And actually you can use two references here. Either you can estimate the sphere moment of inertia of the same parameters, or consider moment of inertia of the teapot parts. Does anyone from jury members need me to convert Russian answer to the CIS units? Thank you, I will not do this. We are waiting for your grades for task number 4. We finished with the theoretical part of the Captain fight, and I think we can now do preliminary results of this preselection part. Can we?
Yes, we can. Just give me a
Super.
second.
So excited. Who is the first? Who is the second?
Yes, I have the results for the theoretical part. So we have following results. Ukraine got 16 points. United States got 14 points. And Russian team got 13 points.
Thank you. It's really tight. Tight result after 4 tasks. So everyone can win this round. Anyway, we have another 2 already experimental tasks for our Captain fight. Now we're gonna to use your physics intuition to be able to estimate some values of some physics parameters. We have the cup. I hope you can see me now, not only the slides. And the plan is the following. Now this cup is empty. And I'm gonna start tapping it by spoon just to produce how it sounds when it's tapped. Then we will fill it with water and listen to the sound which it produces when it's full of water. And your question would be to estimate the amount of water inside the cup. How much water inside the cup? So first, we're gonna listen to the empty cup. I hope it will be heard. Is it enough? I hope so.
Can we keep doing it for a few more seconds? Okay.
Just I'm asking if it's enough. What about now?
Can you please repeat it, but put the micro closer to the cup because we just can hear it.
It's a pity. Give me a sec. Let's try now.
That is still with nothing in it, right?
Say again?
That's still with the empty cup, right?
Yes, it was empty one. Yes. We're just trying to be satisfied with the sound from the empty one. Are you happy now? Okay, super. So now I'm filling it with the water. I know the amount of water I put in the cup, but you don't. And I will produce another sound now, already with full cup. So listen to it.
Maybe closer to the microphone once again.
Okay, I will try to do it louder. Is it okay now?
No, it started out loud, but then it faded away.
Okay, let's try give another try.
Yes, please.
Okay. So your task is, I don't know why you need 3 minutes for this, but your task is to find out how much water is in the cup. Should start your time. I need the number from the US team.
I'm typing it right now. So.
Okay, okay. I see your results. And now I'm not happy of C units. Okay. So the replies from the teams are the following. Ukrainian team gave 100 milliliter. Russian team gave 200 milliliter, and US team gave 2 and 5, 10 minus 4s. What I would interpret as 250 milliliter. I'll send it to the chat. The correct reply is a bit larger than our participants estimated. So it's 270 plus minus 10 milliliter. So no one fit even within the error range. But yes, I added a bit more water than they expected. Please, our member of jury, I would like you to send your grades to Nikolai.
May I just comment? So I think I don't know if it was clear. I sent the SI units after. That's
yes.
of volume, so meters cubed. Just so that there is no big
Yes, I
confusion
think I
about that.
announced it. Yes, I announced it there was. Let me do it correctly in the chat.
I see.
While we are waiting for the capital price results, we have plenty of time to reread your report presentations, finalize them, polish them, find the last errors. I hope you're not getting bored.
So yes, I have received all the results.
Super.
So was it the last task?
Yeah, it was the last task. So now we want to announce the
Great.
final grades and to find out in what order we're going to present in this final fight.
So just a second. Yes, Sonia, you can. I got it. All right. So for the experimental part of the captain's fight, Russian team got 8 points. Ukrainian team got 4 points. United States team got 8 points. So in the sum, we can easily calculate that Ukrainian team got 24 points. Yes. United States team got 22 points. And oh, I'm sorry, I'm misleading you. I'm sorry. It was my fault. Just a second. Oh, the result is very tough. Oh, so Ukrainian team Yeah, Ukrainian team got 20 points. Russian team got 21 points, and United States team got 22 points.
Yes, that's extremely tough. So for the final results, it's kind of 4 for the final task, 4 for Ukrainian team, 8 and 8 for Russians and the US team, right?
Shall we make one more task for the teams because they're so close?
Yeah, we have actually a small reserve task for you. We actually expect that some of you did get this kind of tournament spirit here, this way of living when you cannot sleep well, when you cannot do all the tasks you want to do in time and properly. And actually, when you run the tournament, it works the same way. It's a bit of our disclosure. So I'm starting to share my screen again now. Do you see it?
No.
Not yet.
It's slowly coming.
Okay. What about now? Can you see it now?
Yes.
Super. So our question is about our life routine during the preparation of the tournament. You met 5 chairing person during this tournament, 5 people who've been responsible for 5 tournament rooms during selective fights. You met on the 3 of them, but you get the point. So the question is, you need to estimate how many hours did all 5 of us have slept during last 2 nights. We give you 1 minute for this. I think it will be sufficient.
Is that the total number of hours or the average hours?
Total number of hours for 5 of us for 2 nights. So time is started. Ukrainian team, I need your reply. Ukrainian team, I don't see your reply. Ukrainian team, don't connect match. You have 5, 4, 3, 2, okay. So the replies from teams are, the US team gave results 30 hours, Russian team gave results 45 hours, Ukrainian team gave results 54 hours. You overestimate our disability to run tournament well. Actually, we slept better. And in total, we got 66 hours. So let's consider this tournament run pretty smoothly. And now we're waiting again for the grades from jury members.
So I have received all the grades from all 4 juries, and I'm about to reveal the result. So the places have changed, I need to say. So the United States team got in total 22 points. Russian team got 25 points, and Ukrainian team got 28 points.
Okay, thank you. Is everyone happy with how we run capital fights? Do you have any questions regarding it? Looks no. So super. We can move from this part to the selection of the lines in the tournament table.
Sorry, excuse me.
Yeah.
Was that a physics problem?
It was a problem for the capital fight.
Okay, I see. I'm not the captain.
Thank you.
Does just a question from someone from the team that is quite new on the competition. So does that point count towards is just to define who's going to present or something like that, or does
Yes,
it
yes.
count?
By the capital fight, we now will deciding how you're gonna present in what order and who is making opponent speech for whom.
And does that count towards the final grade in the
No,
final?
it's not added to the final grade.
Oh,
So
I see. Okay.
you get your grades. It is your grades for your report speech, your opponent speech, and your review speech, and that's it.
All right. Yeah. Thank you.
Super. It would be strange if we have, I don't know, around 50% of total grades just decided by the captain fight. So now we move to the selection of your lines in the tournament table. You all can imagine a tournament table. So now we got the Ukrainian team got first place, Russian team got second place, US team got third place in the captain fight. So the Ukrainian team can decide first in what order you're filling the tournament table.
We will choose our order as a second.
Okay, you choose the second team. Russian team, now question to you.
First,
on which order?
First order.
Okay, so US team, you deciding about you got the remaining line. Okay, Russian team, what line do you get? I can't hear you. Russian team, I cannot hear you. What line are you choosing?
We're discussing it now. Just yeah, one minute about.
Okay.
So in first action, we're going to be reviewer.
Okay, thank you. So I suppose it's third line. Ukrainian team, what line are you choosing?
Ukrainian team have chosen the second line.
Second
Russian
line.
team have chosen the third line, and so US team should be in the first line.
Yes, sounds like a plan. Great. So in first round, we have US team acting as a reporter, Ukrainian team acting as an opponent, and Russian team acting as a reviewer. And the US team gonna present us problem number 10, if I'm not mistaken. And you have your time to prepare for your report.
I'm sorry, we said that we want to choose as a second team, not the second line.
Yes. That's sad.
Yeah, I understood. So the order of choosing the line.
Yes, we did this. Okay, sorry, it's my fault. I heard from you second time as well that you choose the second line. Okay, the Russian team, did I get you right? So you're choosing third line for the tournament table, so you're reviewing for the first round, right?
Yeah, we want to make our report in as last.
Super.
Then
Ukrainian team, you're choosing on second turn, right? And what line are you choosing?
The first line.
Okay, change the situation. And US team occupies line number 2. Is everyone happy now? Okay, change the situation. So now in round 1, we listen the report from Ukrainian team. It's gonna be problem number 12. All right? Great.
Just where can I find the lines?
On my piece of paper.
No. Just give me a second. I will share the screen with the table, with the table of the play.
Yeah.
Just give me a second.
Sure.
Yes, team. In round 1, you make opponent speech, so your opponent to Ukraine, and the reviewer is Russia. In second round, you are reporting, and your opponent gonna be Russia, and Ukrainian team gonna be reviewer. And in third round, you are reviewing. The reporter will be Russian team, and the opponent will be Ukrainian team. It's invert what we will see now in the table.
Sounds good.
Excuse me, wasn't the USA going to report the first round?
No, while we play in the captain fight, it's not about deciding who is reporting first. It's about deciding who is choosing the line in the tournament table in what order.
Oh, okay, thank you.
And meanwhile, Nikolai sharing magical table. Ukrainian tip, are you ready? So you need to start now.
Yeah, we are ready.
Okay, start.
Okay. Hello, my name is Ovcharenko Grigory. I'm from Team Ukraine, and now I'm going to report the solution of problem number 12, resonating glasses. According to the statement of the problem, we need to investigate the frequency sweep, which may be observed in a case when we put the two glasses together and they emit some sound. Here, sorry. Here you can see the structure of my report. First of all, I will demonstrate you this phenomenon and qualitatively explain the periodicity of the restoring sound. Then we will investigate the hits. To do this, we will investigate both the frequency and the loudness of the hits and investigate the influence of different parameters of the system. And then we will investigate the cell frequencies of the system. Thus, we could allow to simulate the sound and compare the simulation with the experimental sound. Here you can see our experimental setup. We used a laptop, a microphone, and different types of glasses, wine glasses, usual glasses, and small glasses. Also, in our solution, we used such an experimental setup. We used special fittings for glasses, and we used a stick, which were inserted between the glasses, and thus, removing the stick, we allow glasses to collide. Here we have to say that there is no principal difference between the colliding glasses by hand or using our experimental setup, because in both of these cases we observe the frequency sweep. And for the repeatability of the experiments, we use the stub presented below, above. Now let's explain the reason of periodicity of this effect. As the finger pushes glasses together, they collide and emit some sound. Then glasses rebound but with a lower kinetic energy, and this process repeats until the glasses fully stop. Now let's analyze the spectrum of the sound for the case of multiple hits, and here you can hear the sound. Do you hear the sound?
Yes.
Okay, and in the case of one hit. And you can see that the eigenfrequencies of the system remain the same. They do not change either we have a one hit or a multiple hits. And thus we can conclude that the effect is not related to the change of the eigenfrequencies of the system. It is related to something more complex. And to define why does it happen, we will use such a qualitative explanation. We investigate first of all the usual sound, just usual damping signal, and you can see that its frequency doesn't change. As we try to periodically restore the amplitude of the sound, we also do not observe the change of the eigenfrequency. But as we try to decrease the period of the restoring, we observe on a spectrogram and on a sound the effect of the frequency sweep. And now let's investigate why it doesn't happen. It is well known that if we have a signal with periodically changing amplitude, then this signal may be decomposed to the two signals with different frequencies, which somehow shifted from the main frequency of the system. But in our case, as we mentioned, the frequency of the amplitude restoring changes with time, and thus this frequencies also shifts. And this leads to the frequency sweep, which we hear by our ears. And we, in our problem, are interested in the higher frequency because it leads to the frequency sweep, which we hear by our ear. Also, we understand that in the reality, the sound doesn't behave like this. It behaves something like this because of the damping of the signal. And to investigate the parameters of this damping and the parameters of the change of the frequency, we move on to the investigation of hits. To do this, we assume that during one hit, the angular velocity changes in the constant number of times, and this coefficient doesn't depend on the energy of the glasses. And also energy which goes to the sound is proportional to the difference of energy before and after collide. To do this, we made an additional experiment, and here you can see the dependence of deflection of glasses with time, using which we found the coefficient gamma. Now, using this coefficient, we define angular velocity depending on time. Between the hits, we write down the equation for rotational motion, using which we define the frequency of hits and this dependence of frequency on time. We made the same. For the amplitude of hits, and you can see that this amplitude linearly decreases as the period of the hits. Now let's verify this dependence experimentally. We investigated the time between hits, depending on the time, and you can see that it indeed decreases linearly, as our theory predicts. And we made it for different initial angles of the deflection of the system, and we see that that the same dependence may be observed for different initial deflections. We made the same for the different amplitudes of the sound, depending also on different initial deflections, and you can see the same dependence, also predicted by our theory. Here we investigated the dependence of time of the Hall effect depending on the restoring force, and we changed the restoring force by adding an additional mass to the glasses, and thus we allowed glasses to have a higher restoring torque, and this leads to the lower time of the effect. And we investigated the relative amplitude of sound depending on the deflection of glasses. And you can see that for small deflections, our theory really good predicts this effect. But for higher deflections, we see a divergence, which may be caused by the non-linearities of our system, because at higher amplitude, the motion doesn't becomes linear, and it is lead to such divergence. And we made it for different masses of the glass, and you can see that this dependence also may be predicted by our theory. The same effect we investigate the same dependence we see for the time of the effect on the deflection of glasses, and thus we investigated how the amplitude and the time between hits depends on different parameters of the system. But this doesn't define the whole sound. It defines only the amplitude and the frequency of hits. And to define the whole sound, we have to improve our solution, defining the cell frequencies of the system. And to do this, we move on to the investigation of sound. And here we assume two different sounds which may occur in our system. It's a bending oscillations of a glass itself and the elastic oscillations of the bottom, because bottom also has eigenfrequencies, and they needed to be taken into account, as we will show soon. In our problem, we set such a geometry. We set the radial coordinate system and deflection of the profile from its equilibrium position. We write down the expression for the curvature of the profile and decompose for small deflections. Here we consider the small oscillations of a glass. And using this curvature, we define the density of the elastic energy through the Young modulus and total bending energy for the whole glass. Here also we have to take into account that the glass may bend not in only in radial direction, it also may bend in vertical direction, and we add additional curvature to our system, and thus define the expression for the full bending energy. To write down equations of motion, we also have to define the kinetic energy. To do this, we find the velocity of radial and angular motion, and from the conservation of mass for the whole glass, we define the expression for the kinetic energy. And using the expressions for the kinetic and potential energy, we define the Lagrange function of our system. And using the Euler-Lagrange equation, which is somehow modified because of we have the dependence on second derivatives by coordinate. And using this equation, we define the final equation of motion. It is presented here, and substituting periodical solution, we get the dispersion equation. We get the dispersion equation, which defines the dependence of angle of the frequency on wave number. The spectrum of the system may be defined from the boundary conditions of the loop geometry. And here you can see on the right slide the first mode of oscillations of a glass. And now finally we can relate the spectrums which we obtained in our theory and experiment and compare the sounds. Here is the theoretical sound and experimental one. You can see that they really good correlate, but there are some problems at nearly 4 kilohertz, which we have to take into account. And to do this, we take into account the oscillations of bottom, as I mentioned. We write down the equations of dynamic deformation. Also, we substitute it also in the periodic form and define the solution for equation for a radial function, which is obtained in the Bessel equation and this equation is a Bessel equation, and solving it for the boundary conditions, we get the spectrum, which is represented here. And indeed, we can see that they really good correlate, except of bending frequencies, which we obtained before. And applying this spectrum and summing this spectrum and the spectrum of the oscillations of the glass itself, we obtain the final theoretical experimental spectrum. And here you can hear the theoretical one and the experimental one. I will repeat them. Okay. So in our report, we first of all qualitatively investigated this problem. We defined why does this effect happens. This effect, I will repeat, it happens because of the decrease of the restoring frequency, and thus increase of the restoring frequency, decrease of the period of restoring, and thus appearance of the additional frequencies on the spectrogram. Also, we investigated the hits themselves. Thus defines the frequency of the hits and amplitude. How does the amplitude of the sound depends on time? And we investigated the eigenfrequencies of the system and simulated the sound and compared it with the experiment. And you heard the comparison. Thank you for your time.
Thank you, Grigory. It was a nice presentation and took it in time. So now we have time for clarifying questions to for the opponent team. Yes, your opponent team now, if you didn't get our table.
Hello. So
Yeah,
I have a few
hi.
quick questions. The first thing is, I saw in our picture that you used an omnidirectional microphone. That's correct, right?
Yeah.
The ambient in which the measurements were made, was it acoustic isolated, like for reflections, internal reflections?
Yeah, I understand your question. Like we used, instead of only this microphone, we used smaller ones which were placed in different places in the room where we investigated it to make echoes effects to be neglected one in our problem. We used a room which were in which there were a lot of places. It's like it wasn't the box room, so the echoes effect didn't observe.
I think that was relevant. Another thing is related to the shape of the glass. I see you did a very extensive study, an analytical study regarding the cylindrical shape, but glasses come in all shapes and forms. Did you have any estimation, either numerical or theoretical, regarding, for example, a square glass or a tequila glass?
No, we didn't investigate them theoretically, but we understand that mainly the eigenfrequency may change, like the effects also may be observed, on my opinion, in this case.
Okay. Did you only use glass glasses, or did you use something like metal or crystal or something else?
No, only glass, because in the statement of the problem there was a one glass.
Sure. And do you think this change on the material would affect a lot or a little compared to other parameters?
Yes, I think so. It will affect the gamma coefficient and the eigenfrequencies of the system, yes.
Sure,
Thank you for your reply. Now we have time for the preparation to the open speech.
você tá falando? Quanto tempo? Quanto tempo? Baixou. Não. Vou apresentar sem. Não dá. Deletou tudo. Tudo.
You also can take a 1 minute timeout, one timeout per team if you wish. If no, and if you have any slides, I suggest start sharing them.
Excuse me, I didn't hear you properly, and I didn't realize I was not muted. So sorry, everyone here in the room and in the stream for that. Could you repeat? Sorry.
If you have any slides, I suggest to start sharing them.
Oh, unfortunately, PowerPoint crashed on us, so we won't have a presentation.
Okay, so you can start.
Okay, hello, my name is Carlos Marcio, and I will be opposing the problem resonating glasses. First, I would like to comment a little bit regarding the theory that presented. I think there are many positive aspects in his theory. He did a thorough investigation in many aspects. He investigated the collision between the glasses. He investigated the elastic theory and the dynamics between the oscillation of the glasses. He analyzed the air cavity between the glass and how that affects. However, I think there are a few limitations. The first one is regarding the shape of the glass. His equations work extremely well for cylindrical glasses, and that's great. But again, as I said, I think it would be interesting to at least look over other shapes of glasses, as glasses are not limited to just cylindrical glasses. A suggestion to how he could do that would be to perform a finite element method analysis. There are many even open softwares that could do that, and I think it would be very enriching to the presentation. After that, we move on to the experimental analysis. I think he used very well the tools that were provided to him. So even though we are in a virtual presentation, he could use like the sounds and shared with us the sounds so we could compare not only with our visual sites, but also with our audition, because this is a problem about sound. So being able to hear what was predicted and the experiments was really a great move. And I think it really enriched his presentation. Again, I would like to see a few more variation of parameters. Like I see he varied the glass a bit, but I would like to see varying materials, because that would affect directly in the Young's modulus and the restitution coefficient between the glasses. And I would like to see more videos of the phenomenon running and the setup in the different states that he claimed that he ran the setup. Finally, I would like to go over some of the topics I would like to discuss during the fight. The first one is regarding the collision between the glasses. Sorry, my throat is very dry here in Brazil. The collision between the glasses, how exactly was that accounted? How exactly and when the does the nonlinear effects appear? And I believe he said at some moment that the amplitude decreases linearly, and I would like to investigate until which point that claim is true, because usually when we talk about dissipation in physics, it's usually some sort of exponential. But I think that's a very interesting topic to see. After that, I would like to discuss a little bit more about how the shape of the glasses affect that, and specifically regarding the points of contact during the collision. So I remember in one of his pictures, the whole side of the glass would enter in contact with each other, whereas in a perfectly cylindrical glass, only the bottom would collide, and then it would be much harder to equate the contact mechanics between these two glasses. And finally, I would like to talk a little bit about how the viscoelastic behavior of materials such as glasses affects the dissipation of the system, because usually when we talk about beams or structural mechanic and we talk about these dissipations, we usually look at this viscoelastic coefficient to see the dampenings and to see how it diminishes. And if there's enough time left, I would also like to comment on the waveform, because we saw a lot of predictions regarding the frequencies. We heard a lot of sounds that were correlated to spectrums, but I think it would be really enriching to be able to see the waveforms that were predicted and the waveforms that were measured experimentally, because those could be highly affected by like the capture rate of the microphone, among other things. I believe that is it. I would like to call the reporter for the fight.
Okay, thank you for your opening speech. Now we have time for the discussion between two of you.
Yes, I'm here.
Okay, so first thing, could you go to the slide where you show the theoretical waveform, like the last one before you start getting more, I think it's one of the very first slides in the part of your theory.
Nearly this one, yeah?
Yes, so just so I have an idea, this scale here, the amplitude scale here is logarithm or linear?
It's linear, but like it isn't theoretical waveforms.
It's just to illustrate.
Yes, it's just to demonstrate the effect. Yeah.
Oh, sure, absolutely. If you were to compare this waveform with the actual waveform that we observe when we run it through a program like Audacity or any other sound analyzing program, how would this image like from the right differ from the one that you would see in such program?
From the right, like yes, in the reality, the frequency is higher, of course, because it's nearly kilohertz, and like it would be, you understand, like, and also yes, there's a distortion of the amplitude, but the actual waveform doesn't give us a lot of information. The spectrogram gives more, and so we compared the spectrograms. Indeed, yes, there are decreases of the amplitude. Yes. Sure.
Do you think it is more clarifying to analyze the problem as various pulses of frequencies, or or just apply the spectrogram over the entire thing?
The spectrogram, I have to explain that we investigated the spectrogram of the one hit. Like when we compare the spectrograms, we compared for one hit, but the sounds we simulated for the multiple hits.
Sure.
Yeah.
Absolutely. You also have a prediction regarding how much time it takes between each heat, the time between each heat. Could you put that in that graphic?
Yes, of course. Just a second. Time between heats. Yeah, this one.
Yes, exactly. So in this graphic, I would imagine that the uncertainty in the y-axis would be just repeated the experiment multiple times and did some kind of standard deviation. But regarding the uncertainty on the x-axis, do you not calculated, or it's just too small to be seen in this graphic?
They are small, and okay, you have to understand that the uncertainty along the y-axis is the same for the x-axis, and the uncertainty is small for the x-axis. Like there are
Wait, is it the same uncertainty for the x and
yes,
the
because
y-axis?
of like you have to understand that we define the moment of time when the amplitude increased. And this moment of time along the, like we found the sequence of times. Let me show you the sequence of times and define the time between them and how this difference in time
between each peak, you mean?
Yes.
Sure.
So in the time we have the same uncertainty. Yeah.
So it would be the same uncertainty in the x-axis and in the y-axis.
Yes.
Why did you choose not to plot it then?
They are too small. They are lower than the points themselves.
Oh yeah, I see the scale is different. It makes complete sense, and I agree that we wouldn't even be able to see them. Now I would like to go back to your experimental setup. If you could show us the first picture where is there a computer and the room in the background. Yeah, like the next one, I think. Sorry. Previous slide. Yeah, this one. How big was the room in which this experiment was conducted?
It was nearly standard room, but like we use this soft objects around it, which damp the sound, and thus we didn't have any echo.
What kind of material it was, just so I can have an idea? Because usually when we try to dampen sound professionally in like studios, they do that not only using like the softness of the material, but also the shape. You can see shapes that resemble a lot egg boxes or just saw waves.
Yes, I understand. Like we didn't have such a room, and we used usual sofa and such soft devices, which allowed us to see such effect.
Do you think that?
Yes, finish your phrase. Yes, and we finish the discussion.
No, I agree that it was a pertinent choice, and that echo is not relevant because of that.
Thank you. So now we can move to the clarifying questions from the reviewer team. Russian team, please go ahead with your questions.
Firstly, I'd like to ask a question to the reporter. Can you please open frame number 35?
Okay, sure.
And while opening on this frame, we may see that at the end of the collision, something strange happens to the
Sorry. 25.
Upper one, yeah. So it's something 35. 35. It already.
Okay.
Yes. Thank you. This one. So what happens with the frequencies at the end? Why do we see some principle different from what was before?
Because of the restoring of the sound, because of the collision itself, they
so I think I got
period between collisions becomes comparable to the frequency of the sound itself, and thus.
Thank you. It's clear. Did you try to change the size window in Audacity while making this spectrogram?
Yes, of course. We understand that the spectrogram depends. Yes, we tried. In each case we observe the same effect, like the uncertainty on frequency remains, but like
with different window size.
Yes, we tried.
Can you show?
No, we haven't into presentation, but like yes, we tried.
Got it. Thank you. On the first frame, you talk about restriction coefficient. So did you check it experimentally if it is constant or is it just your assumption?
Yes, we checked it.
Can you show it to prove?
Yes, the experimental group. Wait for a second.
And while you're answering, I'll ask opponent. So
sure.
Discussion, you've talked about the size of the room. So can you clarify what was the important role of this question?
basically, when I talk about the shape of the room, especially in really large rooms, we start to have a very noticeable echo. Like if you are in an empty garage, and these reflections could interfere and create false peaks in the graphic, or false idea of there being more hits or a different frequency being created.
Yeah, thank you.
Okay, thank you. Sorry, you don't have any more time for questions. So you have time to prepare to the review.
So we take a time out.
Okay. Okay, I invite you to the stage, the reviewers team.
So, do you hear me now?
Yes.
Yeah. Dear colleagues, my name is Ivan Palonik. I'm a member of the Russian team, and I'm happy to show you our review of the problem number 12 for data glasses. So let's go to the statements of problem. Where says that we should observe in this phenomenon frequency sweep, and for the first and talking in the unfortunately, in my opinion, reporter didn't explain enough this frequency sweep because as persons who try to work with some audio, they can clearly know that if you have some recorded signal and you try to visualize it in Audacity program, picture which you will get will depend on a window size of fast Fourier transforms that you use. So, because in my opinion, this is the main part which reporter didn't investigate in his program. So, in a few words about main results which was done in the report, is a result type in which consists of glasses and rod. Unfortunately, I didn't make it clear how did he change the size between the glasses in his tab. Mechanically, problem was solved on very good level, so I liked it very much. Also, it was, for example, it was talked about the restriction coefficient, and going to the main advantage of the problem, it's a really good theoretical model. So I liked it very well. With good mechanical explanation based off torque equation, taking restriction coefficients and friction into account. Also good enough acoustic investigation with finding cell frequencies of the system and how sound will change. But there are also some weak points as a report, and part of it is investigation of frequency sweep, especially for changing the window size in Audacity program. Also, wave propagation was not so clear. and parameters of the AS also can be investigated more. Also, I reporter didn't vary enough parameters of the fingers, such as in his setup he could do it while changing the size of the road. Yeah. And it also would be a good point to add. And if you talk about the discussion which was between opponent and reporter, it was more about qualifying question, but it make it possible to better understand the reporter's work. But there was one very good question about the echo and rate of the shape and role of the shape of the plane in which did reporter use it. So now we're going to the discussion, and I kindly ask opponent to continue talking about the question of the echo role, because I think it's important in the phenomenon and it can really improve the reporter's work.
So my main concern regarding the echo is that he used a omnidirectional microphone. That means that if the sound is reflected...
Sorry for interrupting you, but can, while discussion, reporter open frame number 35, and after seeing on it, it will be clear for all why is this question important in the discussion. And so, opponent, please continue.
So, as I was saying, to measure, he used a omnidirectional microphone. This microphone can measure, like, gather sounds from everywhere, any direction. And if there's any reflection in the room, it would be very hard to differentiate between the sound that's coming from the glass and the sound that's coming from these reflections. So two ways to solve this problem would be to get a better acoustic isolation. Although I think that for the dimensions of the room he said, and using this sofa, he drastically attenuated the echo, or use a shotgun microphone.
And can you, the opponent, can you please watch the demonstration of the screen of the reporter? Do you see that there are some something strange on the end of the spectrogram?
Sure, yes, there are some kind of vertical lines.
Do you see that,
you would not expect?
These lines can be result of echoes?
I think it would need to be further analyzed, but I would not discard this hypothesis entirely.
And
I think it's a very plausible hypothesis.
And, so about reporter, what do you think about it?
Which lines? About which spectrogram we are talking about?
About last third part of the spectrogram. You see in
the lower spectrogram or the higher one?
Higher one spectrogram, and its lower part in the end.
Yes.
It's
the
like
assembly decreases.
One big line. So do you agree with opponents that it can be caused by the echo effects?
Which one?
Upper spectrogram, down part of it, last third part,
okay.
Where you have one thick line. Yeah, like you show. No.
Okay, yeah. This one?
A little bit down.
This one?
Yes, this one big.
This is the eigenfrequency of the system. It cannot be related to the echo.
Excuse me, but I thought when you asked me, I thought you were talking about the graph below and not the one above. So I'm not sure exactly what was your question.
Thank you. Oh, okay, I got it. Next, let's maybe. So, okay, next, let's go to the. You wanted to discuss the wave propagation in the glass, as I got it from your opposite speech. So, I can ask you to describe this with the reporter.
Excuse me, could you repeat?
Yeah, so in your opponent's speech, you talk about the waveform and wave propagation in the glasses that you would like to investigate, to talk about it with the reporter. So, could you please talk about it?
So basically, what I want to analyze in that is what dominates in this problem: the effects of the oscillations of the glass itself or the resonating cavity. So I think the waveform would help clarify that, among other things.
And so what's the reporter's opinion about this?
Like, I'm not sure. Okay, we understand that the glass, it's a system which creates oscillations. But the air inside it, it's an amplifier, and thus we cannot we cannot investigate these problems separately. We have to investigate both of them, and in our report we investigated it, and this leads to the spectrogram which we showed. Yes, indeed, both of these effects are important in our problem.
Okay, thank you for this remark. Can I interrupt you with mentioning that we can start now the general discussion, and we can invite team members to the discussion.
If anyone team member wants to ask a question, just write plus in the chat, and I'll ask you about the question. Yeah. So and now, please. Oh, okay. We have a question from.
We have plenty of questions. Yes.
Okay. Can you stay at the 35 slide, please, the reporter?
Which one?
35. That. We clearly see on the experimental, on the theoretical plot that the frequency at the end is increase, and I didn't see the same in your experimental plot. So how could you explain why you didn't have the increasing part of the frequency in your experimental plot?
Yes, this effect may be explained by, first of all, on this spectrogram, in this case, for this special spectrogram, it is not the best one, because on other spectrograms, we observe this effect of the appearance of two branches. And also this effect may be explained by the dense cell frequency, because if you can see that there are a lot of cell frequencies of the system on the experimental plot, and and each of them are having the branches which goes down and upper, and thus we do not, they intersect, and so.
Can you show the plot, experimental plot, with increasing of frequency in your report?
And while the report is opening the frame, question from Marius Barbosa.
Yeah, I have a question. So my question is about the frequency. He says that the frequency sweep is due to the collisions that get more and more frequent. But there is one point. We hear a very a sound characteristic of a high frequency rather than a low frequency. And if exactly in that graph, if you take the time and you find the frequency there, it's a low frequency, right? We have a very sharp sound when we hear the collisions of the of the classes, like something like more than something more characteristics of low frequencies. So I would like to understand why that's the case.
Why we do not hear the sharp sound?
Yeah, the sharp, we hear a sharp sound, but the collisions, if you take in that specific graph of yours, that is a low frequency hitting frequency, right? That's a low hitting frequency. If you take it, should be something about 20 hertz or something like that.
Okay.
Or 100 hertz at the top. So and the characteristic frequencies that should be produced by the cavity should be the order of 10 to the third hertz, right? Depending on, of course, the shape and everything, but the frequencies produced should be much higher frequencies that we hear, because those are sharp sounds, like higher frequency sounds.
Yes, like indeed, yes. So this effect is observed when the time between hits becomes very low, and thus comparable to the period of the signal itself, and thus we observe this effect only in this case. Indeed, in our experiments, we observed only in this case. So you also could see on the spectrogram that only after some time, just before the end of the sound, we can hear this effect. Yes, indeed,
okay,
it's true.
Okay, thank you.
Time is over.
We have to. I'm sorry, we have to finish the discussion. We have 2 more rounds to fight today. And it is time for the conclusion remark.
I want to say thank you to the both opponent and the reviewing team. And there were left some questions which we didn't discuss during the discussion. The main effect is elasticity of the glass itself, and we investigate it to make a simulation. We investigated the elasticity of the collision of the cylinders, and we not instead of the very fast amplitude amplification, we investigated the whole process of the hits, and thus we investigated the like in our theory we investigated the linear dependence of the amplitude, but for final stage we have to make more accurate calculations, and we investigated such a model. Which indeed depends on the main parameters, main elastic parameters, and the frequency, viscous frequency, viscous elastic properties of the system. Thank you for your time.
Thank you everyone for the discussion. We now move to the question from jury members, and I suggest to go in the order, like we can then shift this order. But now we start with Oki, then Pierre-Louis, and Sonia, and then Leandro.
Thank you. I would like to see slide 35, please.
35, okay.
Yes. And my question is about the lower spectrogram in orange and purple. On the right side, we see that there are some divergent lines. Do you think these are real and observable in your experiment?
Like it is hard to observe. We can judge about these lines or only using our spectrogram, and like we have a sound in which if we decompose it using the Fourier series, we observe this picture. Actually, the effect is what we hear by our ear.
Yeah. Okay. Good. I would like to just see the opponent's opinion as well. These divergence purple lines. Do you think that they are observable in practice?
Yes, in fact, I believe that if you change slightly the frame, the ear, as it's called technically, in the spectrogram from Audacity, he could see that very clearly.
Okay, thank you for your answers. Next question.
Thank you, Pierre-Louis. Please, if you have any question.
Yes, I do. Thank you.
All right.
So first one on this slide, what's the scale of your synthetic spectrogram, the lower image, your artificial sound?
Actually, are you
Is
asking
it kilohertz?
About? Yes.
Okay, so
it was a simulated sound. It doesn't matter. Like it is just to demonstrate the effect.
Ah, okay. So it's not directly comparable to the professor. Okay, good. Okay. And another question: did you calibrate your microphones?
In which way? Like it is measured in decibels, and so thus we define the relative amplitude, and like we are more interested in it. So yes, somehow we calibrated it, yes, to the maximal amplitude. And
okay, but do you know the frequency response of your microphone?
Yes, we investigated it as from the company which produced it, and it stopped at 16 kilohertz. It's like it is from 80 hertz to 16 kilohertz. So we are mainly get the frequency range which we are interested into.
Okay, good. Thank you.
Okay, thank you. Then we move to Sonia. Sonia, if you have any question.
Yes, okay, I'm here. So can you go, the reporter, to slide 21? Or just to check your plot. Now, yes, this one. If I remember, you said that going, if you go to the right side, to the highest part in the horizontal axis, you see some deviation. I would say that this is the truth for the highest behaviors curves, not for the first one, which is fitting inside the error bars. Do you have an explanation why it starts to behaves differently from the behavior is not correctly, let's say, described by your model?
Okay, yes, I have an explanation. It is a dependence for the different colors represents dependence for different masses of the glass. And the explanation is that if we have a higher deflections, then the restoring force doesn't become constant. It depends on the angle itself. And thus it is harder to investigate. We have to simulate the motion. Like in our simulations, we did it. Like in our simulations, there were no such a convergence between theory and experiment, and mainly it is defined by the time of the motion of the glasses itself, because of the higher glass. Yeah.
Okay, and there is one question to you, but extended to the reporter and the reviewer. Did you perform all measurements the same day, so the very same conditions of the air, for example? I rephrase my question. Do you think temperature, humidity for the range of frequency you are investigating can affect the results if you took results in different days, on different conditions in general?
Yes, indeed, it may somehow, like as the speed of the sound depends on the temperature, it may change the frequency which we obtain because of there is a different cases of the different like the generation conditions are the same, but the air conditions are different, and thus we have another, I don't know, the frequency states and so on, and it will lead to the change of the frequencies. But mainly in our experience, if we compare them with theory, we made for the same conditions. Like the most experiments were made in 1 or 2 days, so
Okay.
conditions didn't change.
Do you have to add something, the opponent to the reviewer? Otherwise, for me, it's okay.
I do have something to add. I believe that the importance of the sound cavity is really the most relevant in this problem. So I believe that changes, especially in the humidity, can affect a lot because it drastically, at least for air, it drastically changes. Drastically, I mean, in the order of 10%, 20%. It can change density, it can change viscosity, and I really think it can give results difference comparable to the uncertainties of his measurements.
And for me, for you, I also think that if conditions of experiment were changed, it can affect and get huge error about like 5-10% can be caused by different conditions, initial conditions for each experiment.
Okay, thank you.
Okay, Leandro, if you have time for short, we have time for short question, and I would like to ask everyone to be concise.
Please.
I'm sorry, what? May you repeat one?
Not either 31 or 34. '31 was okay. I'd like to hear again the both experimental and then the theoretical sound. I don't know if it's my impression, but in one case the frequency increases and in the other case the frequency decreases with time. Could you comment on that? And this question goes also to the opponent and the reviewer.
Actually, the frequency in both cases increases because of the like we analyzed it using the spectrogram, as I mentioned before. And the reason of this that you hear it in this way, it may be indeed be the reason of the, I don't know, the microphone, the condition of the room in which we investigated the phenomenon. Thus, it may lead to some change in the sound which we hear, not to its real characteristics. Like something like
And can I also answer this question? Yeah, thank you. So I think that it happens because of your air physics. So in your air, you have something like a fast Fourier transformer with specific size of a window, as I talked in my speech. And because of you have such specific window size, you hear the sound differently. It was the same idea I tried to talk in my speech.
Right.
I'd just like to
the opponent team.
that my
Carlos,
my audition is not very good, so without looking at the spectrogram, I really can't differentiate both noises with just my hearing, because I have not exactly the best hearing. So
It's also from the challenger team. I think we have the explanation would be that in the simulation, each hit would just be a delta. However, in the real world, each hit, when you're hitting the glasses, the energy immediately transfers into the glass and into the cavity. So, and at first, the hit would contain larger energy, which means that the energy transfer is large. So what you're hearing is a prominent plate mode. I mean, the mode of the glass, or eigenmode of the cavity. But later on, these mode kind of damps out, while what you hear is a increasing hitting frequency, which lies at a much lower frequency than the modes of the cavity and the glass. So that's why there's a confusing mixture of these two.
Okay.
Competing.
Thank you, everyone. I appreciate your efforts for during this fight. We have another 2. I would like jury members to send your grades to Nikolai during this time. Actually, no one stops us to the next reporting team, the US team, start being prepared to the second round. It is a very complicated job to do a grading of this fight and next 2 fights, so we should give our jury members time to do this with full consideration. Because it's really like, I've been jury members many times, but every time it's like the first one, wow, what I need to put. They were so good, but so many questions, but it's physics. Here is always many questions.
So I have to say that I have received all the grades from the juries. So
Thank you.
we are done.
Thank you. We can now move to short. I ask you to be short and concise comments from jury members. Let's start from Pierre-Louis, then Sonia, then Leandro, and then okay. Well.
Oh, thank you. Well, very trying to be brief, but I liked the execution by the reporting team, but it could have been made better. The Russian team made this perhaps a bit more clear than the USA team. But in general, I liked the solution you presented. And well, just a comment, I felt like the reviewers were a bit more opposing than reviewing for some part, but that may sometimes happen. But try to more. I mean, you focused a lot on the reporter, not so much on the opponent, at least from what I saw. I'm done.
Now is me. Sonia now. Hello, it's me now. I don't know. Okay, I go. Okay, in general, I liked the discussion. Now, I already saw the Russian team and I already commented on this. they seem sometimes what was said before by Pierre-Louis is they are a little bit aggressive. So maybe when they want to be a reviewer, they seems to be opponents. But okay, I saw also in the other fights. you should find to find out this to change this. For the rest, I found however the discussion fair, and I liked the slides. They were complete. Sometimes many formulas. I said before, sometimes it's better to avoid the intermediate formulas and just show the result. We believe that these are coming from something you did. For the rest, it's okay.
Yeah, I think it's me now.
Thank you. Yeah. Sorry, it's my sound problem.
Sorry.
Yes, go ahead. Yes, Leandro, sorry.
Okay, so I would like to agree with both jurors that talked before me, and I'd like just to stress that there is no way someone can follow a presentation so dense in equations and so fast. We had 35 slides in such a short time. It's humanly impossible to follow. So I think you should pay attention in clarity and bring the main ideas rather than put all the details forward. Nevertheless, the opponent did not help very much to advance the discussion because they focused on very particular points rather than helping advance the general discussion. And the Russian team, again, they were very aggressive against the reporter, rather than helping the discussion to evolve to a better understanding of the problem.
Thank you for your comment. Yes, okay, your comment, please.
I agree with what Leandro said. In addition, regarding my question about the reality and possibility of hearing divergent frequency, while I believe that the phenomenon exists, I think it's unlikely that you would actually get to the end where the frequency becomes so low that the glass vibrate with the same frequency as they oscillate. It just doesn't seem possible to me, but maybe I'm wrong.
Can I just do a quick clarification?
Super, thank you. I hope no one needs any break.
No.
I hope so. That's great. Super.
Can I just
so
make
we
a
can move to
super
round
quick
2.
comment?
In this round, super quick. Yes.
Super quick. Yeah, no, I met Team Russia. I found they were a bit opposing, but also when it came to mediate the discussion between everyone and the chat, I found you did a great job. So that part of reviewing, I really liked.
Thank you for your comment. So now we move to round 2, and in round 2, as I said, US is reporting, Russia is making opponent speech, and the Ukraine is reviewing. Whenever you're ready, please share your screen and start.
I'm ready.
Yes, but also we need your slides.
Right.
Great. We see some.
Yes. We can
go ahead. Yeah.
Okay. Let's talk some physics. All right. Hello, everyone. I'm representing Team US to present problem number 10, hail, where we're asked to extract as much information as possible about the shape and dimensions of a metal container from the sound produced when dropping small objects into it. So let me first break down this problem for you. We treat this system. We treated this system. We treat it as a system with input parameters of a small object, a metal container, with mechanism being the object dropping into the container and producing sound on contact. And of course, the output would be the spectrum of sound or the eigenfrequencies. So in this problem, we're actually given the spectrum of the sound and we're expected to reverse engineer and find out the unknown shape and dimension of the metal container. Yes. So here we can begin by building up the theoretical model, since this inverse problem is not so obvious on the first sight. So we can make a simplification to our acoustic system. So we can think about the metal sheet vibration from the contact. This vibration will transfer energy towards the cavity inside the container by this fluid structure coupling. And as a simple model, we can treat the cavity as a shortly driven damped oscillator of some single frequency. So we're looking at one mode of the cavity. And we can see from this graph that with this high frequency driving force, which is basically the metal sheet vibration in the beginning, after it damps out, the cavity quickly restores to its mode frequency, which is validation for us considering the cavity modes as our main object inside the sound spectrum. So to model the cavity, I modeled it as a open cavity up top, and for the rectangular case, we went with the pressure wave equation, where we have the cavity dynamics governed by the wave equation of the pressure density, and we can quickly Fourier transform it into the frequency domain and get the Helmholtz equation of the hth Fourier component sinusoid. So with the correct setup of boundary conditions, we can then seek a eigenfrequency solution depending on L, M, and N. Each are some mode number correspondingly, as well as the dimension of the cavity, X, Y, and Z. We do similar treatment for cylindrical cavities, where the solution contains the mode number indicating the solution of Bessel function because of the unique cylindrical shape of the container. So we're now equipped to reverse the system. So given this function, given this equation of parameters f, which is the eigenfrequency, and L, M, N, which are corresponding mode number of that specific eigenfrequency, as well as the dimension of the cavity, these are the parameters that's involved. So if we're given the first F, L, M, N correctly, what we're left with is a equation of plane, if you can notice, of X, Y, and Z, which is to say that this on this X, Y, Z coordinate, at somewhere on this plane, we have the correct solution of our dimension of this cavity. And now we just stick another eigenfrequencies into it with a corresponding L, M, and N, and sure enough, we get some other another plane that crosses it at a line. So this shrinks down our actual solution to a line. And as you can see, if we add on another mode followed by its mode numbers, we can identify this unique solution in the first quadrant, which will be the dimension of the XYZ axis projection will be the dimension of our box. So that might look like a long shot, but let's see what the experimental analysis tells us. So we use a few cylindrical as well as rectangular objects. And the setup of the experiment is that we immerse the cavity inside water to damp out the plate modes, or the modes of the bottom plate and the walls. So as we can see, we identify some plate modes and cavity modes. Plate modes on the left side of the graph, where this is this bean can inside on some solid support. And as we can see, it's drastically damped, and now cavity modes are exposed when we immerse the cavity inside water. So upon making measurements, we can notice that for across different boxes of different dimensions, we see some dominant frequency at the lower side of the spectrum. So we can make an educated guess here. What it is it probably is the quarter wavelength mode of this open cavity, because that's the lowest frequency mode we have. And what that corresponds to is actually like in my frequency, in my eigenmode solutions, are the solution when L and M equals to 0. So there's no, so the mode number in the XY plane are 0 and N equals to 1. And this will give us a direct relation between fundamental frequency and the depth of the cavity. And in fact, this is how our US team solved the water filling the cup problem. Yes. So yeah, using the fundamental frequencies that we found for each of the cavity, we calculate the depth of the cavity that way, and we find out that our calculations are very close to the actual depth that's measured. So now let's review the method, this inverse problem method. So we have conquered one dimension. So the old system no longer exists, and we basically reduced our dimension. So if you think about it, we now have a correct matching of F, L, M, and N, as well as a knowledge of Z. So we have an equation of line on the XY plane. And after we reproduce the same process, and we will get a crossing in the first quadrant where we can identify as the solution. And of course, as more lines are fed to this graph, we would expect crossing at the same place. However, in the real world system, there's error does occur, and it's inevitable. So these three lines will not, it's almost impossible that they cross at the same point. Rather, it will display a cluster of 3 points in this crossing pattern, so a triangle pattern. So knowing this, we can quickly measure the first 3 eigenfrequencies of the cavity from the spectrum output and seek for a numerical solution. So with these Fs given, we will match different sets of L, M, and N, these mode numbers, to it, so that we can construct a modal equation. So let's, since these are the 3 lowest frequency, we let L, M, and N each have 2 degrees of freedom, so they can be 0 or 1, and N being 1 or 2, just by the structure of the equation. So that will give us 3 choices of F and 2 choices of L, M, N each, so 3 times 2 by 2 by 2, minus the 3 correct sets of equation lines. So that all the rest are going to be false solutions. So after what's done, we can analyze the crossings of each of these equation lines, noted in the dots, as dots. So we first identified that a lone point is very unlikely to indicate the correct dimension. Secondly, these 3 by 3 parallel points, what they would indicate is most likely some horizontal Y modes crossing some rather vertical equation lines from previous insight of how the equations of the lines contours usually direct. So that leaves us to the left lower corner, which is the which is exactly the geometry that we expected. And finding the centroid, it will give us indicate the true dimension. And as we can see, the result from calculating the centroid is also rather close to the actual dimension measured. So we do similar treatment for cylindrical cavities, and where on this XY plane we have depth and radius. So it gets a little more messy in this case, where in this triangle the 2 points are easily identified, but the third point could have multiple candidates. And of course, the upper and lower points, these suggest crossing with some horizontal mode, so they're not considered. So we hereby make do two different predictions, and each predictions are somewhat close to the actual dimension of the cylindrical cavity, but each are not exactly accurate. So this is the could be a caveat for this numerical method. Yes. So finally, some further insights for the improvements to be made. I can explore other geometry such as half sphere, so that I can, in the end, this method will end up telling you, like if the cavity is probed to be more like a square or more like some ball-shaped cavity, and the model, and we can model the problem from some other mathematical perspective. Maybe that will give us more physical intuition in how this happens. Moreover, I can further study the effect of the metal structure dominant resonances and investigate the coupling in between, which would be another fascinating problem. And yes, thank you very much for listening, and I'm open for any questions.
Okay, so hello. My first question is, please open your slide with the experimental setup photo. So am I right that you submerged your vessel with in water? Yes.
Yes.
Okay.
Yes.
Was there additional weight on the bottom of this can, or it was freely floating in the water? Did you control?
Right. So there are strings attached to. There are like ribbons, like circular ribbons attached to the bottom of this heavy block that we can basically use that to hold the cavity down.
I got it. Thank you. So at which point did you measure the frequencies shown on your
near the surface of the cavity?
And the microphone was directed. Microphone's direction was straightly into the can.
Yes, the microphone position is.
Okay, and a few questions about the objects you were throwing at the bottom. So what are they? You didn't mention them at all in your...
The object at the bottom?
No, which objects did you throw into your can?
Oh, yes. So yeah, that's a very good question. So yes, so the object I threw in my can is actually it's actually a 6 millimeter diameter aluminum bearing, so BB bullet. Yes.
Okay.
And it's a educated guess, I suppose, but it also comes with some simple analysis. So there are some few candidates. For example, there are ping pong balls, plastic BB bullets, and aluminum ones.
So
and
did you experiment with the ping pong balls? Or you just...
Yes, I did, and the result is that ping pong balls have very messy spectrums, and the reason for that is that you can think about like large volume objects. Their deformation takes longer time. So instead of this response being a delta function, it'll look something like this shape below.
Okay, thank you. And
Thank you, guys. Thank you, guys. Thank you, guys. I have to interrupt you now. And
yes.
You need to prepare, have your 3 minutes to preparation.
Yeah, thanks, Matthias.
If your slides, you have now your time to share them.
Okay, so good evening, dear participants. My name is Ivan Kolesnikov, and today I'll be opposing problem number 10, HAIL. So firstly, I want to do a brief report overview and the things that the reporter did during his research. So firstly, he introduced his theoretical part as a dampen oscillating model, and he applied Newman's and Dirichlet conditions on the edges of our container, which are equal to 0. But I quite disagree with this approach, and we will strongly discuss it a bit later. So the cavity was modeled with the Helmholtz equation, which I think, of course, may be used in this case. However, it doesn't include the natural frequencies which are appearing because of vessel resonance. So depending on the shape, the additional frequency should be added in the model. And also, during his research, he investigated cylindrical and rectangular shapes and solved the inverse problem to determine the height of the vessel. However, in my opinion, the problem statement was asking for a shape of these containers and dimensions. So I think this part of the research is under investigated. So as I said recently, the reporter solved the inverse problem for a parallelepiped case, investigated 3 different box sizes. However, we didn't solve the experimental results for all of them. They were just presented only 2 of them at his experimental results. And the numerical reconstruction was presented, and the clusters and that the same eigenfrequency may relate to different shapes also was presented, and I think that this point was investigated quite well and detailed. So now let's move to some report summary. So the points which were really strong in this solution, and some points I would suggest to improve. So the first strong point was that qualitatively this phenomenon was presented by a dampen oscillating model, which I think might be the case if we modify the experimental sub presented by the reporter. For example, we can my main claim to the experiment which was conducted by the reporter is that I think that water submergence of vessel is quite incorrect in this case. For the first, if we drop a steel ball or aluminum ball, which was, as it was said by the reporter, after it collides the bottom of the vessel, for the first, there appears some oscillations. For the second, the water which was pressed out by the vessel, water level increases, and it also influences the eigenfrequencies which appear in this case. So I would suggest just a simple experimental methodic. So we can define the height of the vessel just by finding the time between we release the ball and the first sound which appears. It's quite simple, but this is also the method to investigate this solution. So the strong point with the experimental part, in my mind, the main advantage of the experimental investigation was the cluster investigation, and that the reporter showed that there are, of course, different, for the same eigenfrequency, they may appear some other, it may accord to different shapes. And one more, and a few more things I want to do to improve about the experiment, that I think the reporter may, for the first, increase the reproducibility of the experiment by controlling the temperature and humidity because it strongly influences the sound speed in the air. And also, I would suggest to investigate different shapes, exactly shapes, not the heights, but shapes of container, which we'll discuss later, and its material because it influences the decay rate and the speed of sound in the material, and also where the material of the object would drop and the location which would drop. So if I drop it at the near the edge of the container or in the middle, in my opinion, the results will be completely different. So I think that there are so many problems, so many topics to improve in the experimental part of the report. However, the theoretical part, according to the reporter's assumptions, was good. So now I want to move to the discussion.
Yep, that's a very, thank you. That's a very, very thorough breakdown. And I want to make some comments as well as some part that I do agree with you. So at first, I want to comment that we like the mode frequency I solved that lacks for the Bessel function solution. That one I assumed it to be a perfect rectangular cavity. So there is no square modes involved at a steady state dynamics. It will be an exception, of course, if you try to like blow air into the cavity to create some dynamics. Yeah, and secondly, you're talking about the gliding and the buoyancy, how they would affect the how the displacement of the cavity would really cause the change of eigenfrequencies. So yeah, so if you think about it, it's I would like to give you a simple green functions model. So if you think about this small object dropping as a delta input, then the response, the green function would be the x. There's no displacement at t equals to 0. There will be a discontinuous velocity. So what we do is that we only take the sound spectrum, the sound file at the first very short regime where all the energy is observed. So that effect can be minimized.
Mainly, you were talking exactly about the first point I wanted to discuss. So you're talking about how does the buoyancy and the position of the vessel in the water influence the natural frequencies. So according to your theory, you just stating that the Dirichlet condition and Newman condition at the boundary is equal to 0. However, do you agree that the vessel also starts to resonate according to the wave that was according to the perturbation caused by the ball drop at the bottom?
Yes, that's true. That's true. There is some dynamics.
Do you see that in your case? Of course, in your model, don't take that that is possible. However, in reality, the resonating frequency of the vessel, which was inflicted by the ball, will change according to the depth that the vessel is submerged into the water. So,
yes, I agree. So basically, yeah, the ball dropping inside would definitely change the aerodynamics away from the steady state. So yes, that's very, very good perspective. So I think what I can do to that is basically decrease the size of the ball because my model is based on the steady state approximation. And you actually brought up a point about the defect in my modeling in the way that like my method, it doesn't really predict what shape it is. I also think that's a good point because you pointed out that what I can do is that I can basically trace from the solution. It came to me that so I can instead of seeking for the dimensions immediately, I can look for the boundary conditions because that would but so it would be amazing because that would generalize it totally.
Yes. So
however, it could
exactly what I'm talking that the method you're using boundary conditions just don't allow you to predict the shape. So you just mentioned the ball size, and that's the second point I want to discuss. So please open the slide you showed me during
sorry, I'll do that in a second, but just a quick comment. So I thought about that. The boundary conditions, looking for boundary conditions requires us to trace back the dynamics in time. And if we have something like a delta, delta force, like activating all the modes, it might be hard to do because we're tracing back a solution at t equals to 0 that equals that delta, which is kind of not.
While you're talking, can you open the investigation of the ball radius?
Yes. Yes, that's
so. During our brief discussion in the clarifying questions, you mentioned that there appears some strange effect, some weird effect, according if we take the if we increase the ball radius. So, what do you think is the main reason for that? In my opinion, is that you changing the ping pong ball is much larger than the steel ball from the bearing, so it strongly influences the volume of the vessel, and as a consequence, changes the volume frequencies which were created by the ball drop.
right. So you were you saying that I should use a smaller ball? Is that the point, or did I miss your argument? Yes. Yeah, so this is a steady state approximation. Yeah, also I didn't finish answering your question on the choice of small object. So I compared basically an interpretation the two Green's functions. The second one is not really a Green's function. It's an integral. So this is a X response, and as you can see, it is not totally a single beautiful eigenfrequency of cosine. It contains some t cosine in it. So that is what I assume to be the cause of this messy spectrum. Yeah.
Okay.
Thank you. We need to interrupt your discussion at that point and invite the reviewer to your discussion. So now the Ukrainian team, you have time for your clarifying questions.
Thank you. First question, in your theory for rectangular cavity, you use the boundary condition for air that it do not flow from the upper boundary. Do you believe in this boundary condition?
Well, in fact, the air in my boundary condition, it can freely flow. So I would like you to notice that P of H is actually not pressure. It's the pressure. Well, P of H is the pressure density, which means at the upper surface there's no pressure. So basically, you have zero impedance condition. So air can freely flow, and the rest of them are sound hard boundaries. So as you expect. Yes. And also the same same treatment happens for the cylindrical cavity, where I have the Dirichlet boundary condition on the top. Yes, at R equals to at the top level, as you can see the third line. So and also some because of the symmetry inside the cylinder, you also have Dirichlet boundary condition in the azimuthal direction.
Okay.
Yes.
I understood. Second question, could you please show me any spectrogram? Maybe 31st.
Yes, spectrogram wasn't a big part, but yes.
Okay, in the slide, for example, 31, maybe.
31. Wait, I only have 20 slides, I think. Oh, yes, okay. Yes, here, okay.
Yes, it is clear on the spectrograms that frequency is lower than 20 gigahertz. I don't believe in this result.
Oh, well, so why is that the case? Why don't you believe it? So I want to clarify that these are cavity frequencies. So with a certain cavity dimension, with some dimension, you will have like frequencies within like about 1,000 to within 10,000 certainly gigahertz hertz.
Maybe.
Oh yeah, and above on the top, those are, yes, you're right. Sorry, I had a misunderstanding there. So on the top, those are actually not cavity frequencies. They're a display of the metal, the frequencies of the metal structure itself. Yes, that's a good cap.
Thank you. Now the reviewer is preparing, and I do remind you that during the clarifying questions, you need to be short and concise. Don't move into deep details.
Okay. Can I conclude now?
Is that preparing? We have now preparation of the reviewer.
Oh, okay.
You will have your 10 minutes of the discussion, so really you have enough time to share any opinions. You have plenty of room for this.
Okay, yes. So I would like to I would like to
No,
point
dear
out.
reporter. No, dear reporter. Now the reviewer is preparing for their speech.
Yes, sorry about that.
So
Yeah.
when the discussion starts, you'll have all your time for doing any remarks. I'm sorry for interrupting you, but we're following the timetable of the round.
Yeah, my bad. I was not familiar with the rules.
And meanwhile, Ukrainian team will wait you on the stage. Ukrainian team, we do need you on the stage.
Sorry, was there a question?
Ukrainian team, we don't have you on the stage. We need you here. I will start your reviewing time now.
Can you exchange the demonstration screen to our, because we cannot open it?
Yes, it may happen because you have on the one screen.
Okay, I can start.
Yes, sure.
Okay, my name is Marko Gurisenko, and now I will review the task number 10, Hell, and now I'm going to describe the work of the reporter. So we see a clear qualitative explanation as a model and theoretical investigation, where the reporter write down the Helmholtz equation and obtain it only for the some vessel, and then he carried out experimental verification, but not all system parameter was investigated. So we've seen a clear theoretical model. The higher agent frequencies were investigated. A very good experimental setup provided, and investigated the dependence on the height and the radius, and the radius of the vessel, but not all vessels parameters were investigated, such as different geometry, and there is a questionable boundary condition in the theoretical model, because there are no such as easy as the reporter said. The agent frequencies of the vessel were not investigated theoretically. In particular, we didn't get fully information about the geometry of the vessel from the theoretical investigation. It's such a devices how to do this, but not the full description of this process. We didn't see any numbers on the slides, and haven't seen description of the plots. And many plots were didn't understood of our team by our team. So let's go to the opponent. There is what he did a good clarification question about dropping object parameter and experimental methodic. Mentions that game growth model is not fully applicable. That says that game growth model is describes only oscillation in R. Mentions that reporter just solved inverse problem, and mentions that really not all important system parameters were investigated. Okay, well, let's go to the discussion retailing. So opponent asked about the influence of the water used in the reporter experiment setup, and we think this really influences the process. Then he asked not a very good question about how both change the aerodynamic flows inside the vessel. We think it is not really important one, and then we want to discuss some following discussion topics, such as boundary condition in the theoretical model, and the agent frequencies of the vessel theoretically, and
that's all of my that's end of my review. Let's go to the discussion.
Yes, so I want to point out that you were saying that you're a little disappointed that only my eigenfrequencies are solved. I actually, so what I didn't show you is that in order to solve the eigenfrequencies, I have solved the full equation. So you have eigenvectors, which are the waves, but they're not what's at stake here. And eigenfrequencies enough to tell me informations. And also, when you say that not all like eigenfrequencies are considered, yes, I realize that it could be like there could be other ways that I can make use of the full structures of the all eigenfrequencies, but in this way, actually, this is not a disadvantage because the lower degrees of freedoms I give to these LMN modes, actually, the less bad points, bad solutions I'll get. I can show you in a minute. Yes.
What opponents think about it, about eigenfrequencies of the West?
Sorry, could you repeat that?
And what opponents think about it?
Okay, so as I was saying during my discussion and the report overview, according to the reporter's theoretical model, we can distinguish the eigenfrequencies created by the volume because of the volume of the vessel, but not because of the surface, not because of the side surface, so not the walls of your vessel. However, in the perfect case of reporter's model, this may be true. But in the real life, in the real experiment, of course, there will be significant influence. So the resonance of the vessel will also provide us some information about the shape and dimensions of the container, and may also influence the measurement of the height because of the echoes that are traveling inside the vessel. And also,
yes, I agree that. Sorry to interrupt, but yes, I completely agree. So I actually focused on plates in the beginning because I wasn't aware of such a good thing that cavity is. So yeah, I end up deriving a relationship between the dimension at the bottom plate and the thickness of the plate, as well as, well, given the Young's modulus, the type of material. But that did not really tell me much except for the bottom dimension of the cavity. Okay. But yes, that's also a very interesting
and about
thing to
your model. What do you think must be the ratio between a volume of the cavity in the vessel and the size of the vessel due to we can use a Gelmgom's equation, or the ratio must be between volume of the cavity and wall size of the vessel.
Oh, so are you asking basically the thickness of the walls?
Probably yes. Right.
Right. Yeah. So that's something that I was not able to come up with a good scheme to characterize. But like a qualitative observation I had from measuring not only those four objects, of course, for many objects measurements is that the thicker, the sturdier the wall are, the more dominant the plate mode, what I call the metal modes are, because they're better at storing the energies.
And what the opponents think about?
I think I'm sorry for interrupting you. I think from this moment we can invite all team members to the discussion.
Okay. May I just raise a topic to discuss? What's on your cluster diagrams, which you've been presenting in your report, what will change on a qualitative level if we include the influence of the vessel resonance and the surface eigenfrequencies? What's the qualitative intuition behind it?
Right. So the intuition. So it would, if you include that, so you're suggesting something between a rectangular cavity and a cylindrical cavity. So you basically. So I guess there's component for each mode. For each. Yeah. Sorry. For it would be nicer if I can use my slides.
But these diagrams.
Sorry.
Can you please open these diagrams?
Yeah, can someone
think
stop sharing so I
You
can
need
open the
to switch off this slides of the viewer.
Yes, thank you. Right.
So the question is, in the case of these additional eigenfrequencies, how do you extract the dimensions from your cluster diagram? Or
Yes. Thank you for pointing that out. Yeah, I was about to explain that. So with extra mode numbers, is that your question? Yeah, that was mentioned earlier. So with more mode numbers, what you get is more error. And why is that? It's simply because this number right here. Think about it. If you have 3 degrees of freedom for L, M, and N mode, you would end up not with like within 100, but you would have like thousands of lines to solve. And you will end up with something like this when degrees of freedom is 3. And you want to find a cluster of triangle and all these points. So that's not
exactly what I was looking for. So we have a question from the audience.
We have the viewing team is a question. Reporter, have you tried to change the position of the fallen of the object?
The position of the object?
Yeah.
Yes. So here's the thing. When I did droppings, these are random droppings over different areas. So I actually did it in the sequence of like center, sides, and everything. So I made sure basically everywhere is covered. Basically you have to believe me that my result says that at least for these 3 fundamental frequencies. Sorry, I'm just scrolling over. So at least for these 3 fundamental frequencies, dropping it anywhere would not change that for the cavity.
Okay, question to the opponent team. Do you think that it is important which point at the bottom we are pulling our object, or are we pushing it to the wall?
Can you please repeat the question? I didn't
Does it depend on the to which point do we put our object, or do we put it on the walls?
To which points?
So which if we drop it at the bottom or on the walls, basically.
So you're talking about do we observe different results depending on the location the ball drops at the bottom? Am I correct?
Yeah.
So yes, of course it will, but in the reporter's approach, we won't see any difference. However, the frequencies which were appear because of ball collision with the bottom surface, of course, will depend on the location. Like in my mind, the amplitude of these waves will be higher if we drop it in the center of the glass. However, it may depend.
Okay, I want to clarify if the Russian team, did you ask all your questions? I see in the chat you have some discussion.
I want to ask question and then wait time when reviewer may me to do it.
Yes, of course.
Oh, thank you. Dear reporter, can you open slide number maybe 19 or 20?
Yes.
20 will be better, yeah. A little bit misunderstand what you have on your axis in the right plot.
Yes. So sorry, the axes are poorly drawn. Yes, but they're the same axis on the left and right. So
dips and R, and you built these points from the spectrogram, yes?
Well, so from the solution, so I have a spectrogram.
So from the solution.
Yeah, I have the eigenfrequencies from the spectrogram. I then take the eigenfrequency. Sorry, yeah, I went over that a little too quick. So I took basically the eigenfrequencies.
So I understand. Now for me it's clear. Thanks.
Yes. Oh, okay, great.
Okay, shall we stop the discussion at this point and now move to the concluding remark from the reporter?
Yes. Thanks, guys, for the kind and insightful reviews. I especially agreed with what the Russian teammate pointed out, that I can backtrace not the shape, but rather the boundary condition first, based on the solutions. However, it's kind of hard in the current modeling since since like I would have to basically do a trial and error boundary condition. I do kind of robbing boundary conditions for all of them and do trial and error to find out. But that is a promising way to develop this. Yes. So to conclude, I would like to restate that I did this by first understanding this the system and response, and then used the recorded eigenfrequencies as part of the spectrum to inversely solve for the cavity dimensions. And also, essentially, I can tell you if it's more rectangular-like or more cylindrical-like. Although this method is still not too non-deterministic because of the lack of physical intuition, but mathematical approach has gotten us here.
Thank you. Thank you very much. Thank you everyone for the discussion. It was interesting and deep. So now we move to questions from jury members. Can we go in the order now, starting with Sonia, then Leandro, then Oki, then Pierre-Louis?
Yes.
Sonia, do you have any question?
Yes, a curiosity. So to the reporter, he said that he wants to investigate also a spherical shape. Now, I'm wondering this: when you have a cylindrical shape, you have the basis and then you have the walls. So they are sealing. They are sealed together. While when you have a spherical one, there is no sealing at all. So apart the differences because of the shape, are you expecting other differences due to the sealing side? And this is also to the opponent and the reviewer.
Sorry, if I understood it right, you're asking about what if we have a closed cavity?
Yeah,
I
repeat the question. So you still
yes.
want to investigate a different shape, okay? Now the difference between, at least as I can imagine, the difference between a half sphere and what the cylindrical one is that when you build a cylindrical one, you have the basis and then you have the wall sealed.
Right.
Okay.
Oh, right.
So
I see.
additional thing, which is not exactly the shape, only the shape. Okay.
Yes.
Unless you are not using a cylinder with no sealing walls. Okay.
Yes.
Just a smooth surface. Okay.
I
so
understand now. I understand now.
Part, of course, the differences you are expecting because the shape is different. But can you estimate, or do you have the feeling that the fact that there is this sealing part, the sealed part in the basis can affect the problem? And okay, I was asking also to the opponent, to the reviewer.
Yes, I have a little bit of insight on that, and I would like to share with you. So for the seal, so the reason I haven't been able to derive the modes for the spherical ones, half spheres, is because the half spheres includes a Bessel function whose solution has complex value. So it's a little different. But so I guess the point I was trying to make by talking about half sphericals is that by now I have observed some relation between, if you will see, the dimension of the cavities, Lx, Ly, Lz, or R and D, or R and Lz, and the mode numbers, as well as frequency. So they kind of behave as like somewhat linearly, because there's a square here, and there's a root out there. So by looking at spherical, which has even more symmetry, I would like to generalize some like simple, as in some sort of linear estimation of dimensions in terms of mode numbers and frequency. So that would be the eventual goal. And I think what Team Russia proposed, looking for the boundary conditions, that could be eventually the way to get there. Yes.
So now I want to raise my opinion.
I still want to, can you give me a minute? I still want to remind, try to be short and concise, okay?
Yes,
Don't
yes,
give long
okay.
explanations.
Yep,
Thank you.
okay, please proceed.
The point I want to introduce is that in the reporter's approach, if we assume that the boundaries are not oscillating, so we can use the Helmholtz formula, which depends on the volume of the air which is involved into the oscillation. So firstly, if we exchange the straight corner of the cylinder with a smooth half sphere, it will inflict the volume involved into oscillation, so it will change the frequency. If we take two vessels with the same volume and include the Wells impact, of course, there will be different geometry, so the eigenfrequencies will be different. That's all. Thank you.
Okay, yeah, our team is reviewing team. We think that indeed the different shapes, such as hemispheres and the cylinder ones, changes the cell frequencies of the system, even for the same volume of the vessel. And indeed, reporter have to investigate this effect, like the dependence of the different shapes and the different parameters of the vessel itself, but yes, they change the eigenfrequencies as they change the result which the reporter's theory gives us.
Thank you. Now we move to Leandro's question, if you have any.
Yeah, I have more than one, but one of them is more important than the other. So I'll start
Go with
by
it. Yeah.
I'm a bit disappointed by the whole discussion because the proposal of the problem was to extract as much information as possible about the shape and dimensions of a metal container from the sound produced when dropping small objects such as peas into it. I will state again the questions because I didn't see the answer in the presentation, in the opposition, and in the report. How much information and which information can you get from the spectrum obtained when dropping small objects such as peas into a container?
Yes, the dimension, assuming we know the type of cavity.
Did you show the dimension for anyone obtained from a spectrum? I didn't get it.
Most certainly. Sorry, I must have blown by too quickly. So yeah, so here is what it looks like. So for a rectangular shaped cavity, my estimations are below and actual are on the top.
But there are no error bars. There are no.
Well, so the error bars. Here. Yeah. So the actual dimensions are done by measurement, just by measuring with a caliper. And the prediction, I guess I should have added error bars on it. So the deviation would be the error bars would be the deviation of these 3 points with respect to.
Again, if you only have the spectrum, could you get the shape and dimensions of something? I didn't see you comparing different spectra of different objects.
Right. I'll have to assume the shape of the material.
Okay,
but also, sorry, just real quick, but inversely, and we're inversely solving this, we're throwing just with the spectrum, then we can basically fit it to the two approaches with cylindrical and with rectangular and see where this three cluster emerges.
But what if it's oval or star-shaped or boot-shaped?
Yes, this is hasn't provided a solution for these irregularities. Yes.
Other teams?
Okay, so I just want to leave a short comment. So you're stating that, okay, so the problem statement really depends on methodology. So there was asked, how do we extract information and what kind of information do we get? So using the reporter's approach, we can extract only the height, but not the shape. And that's the issue of the methodology. However, this part of the report that we can get some information about this was particularly done. So that's what I was talking in my opposition.
If you don't mind.
Ukrainian team?
Okay, yeah.
Yeah, also our team thinks that mainly reporter defines the estimation for the length, like from the spectrums, he didn't can fully define the shape of the vessel itself. It's just some kind of estimation.
Right. This is an estimation. Yes. Oh, sorry. Yeah.
Can we move to to okay and Pierre-Louis with short questions, please. Okay, you first.
No question, there's no time.
Okay, thank you. Pierre-Louis, if any short, I would allow.
Thanks. I have
Okay.
a short one. What's the quality factor of your cavities to the reporter team?
Right, I did not pay attention to that mainly because energy was not quite the issue here. So I would like to, yeah, so the sound spectrum, well, the sound signal is like this, and we only cut right before the drop and right after the drop, because all we care about is the eigen frequencies. So the first three modes will offer us those solutions. So
okay.
Yeah.
Thank you. Yeah, unfortunately, we don't have time. Later, I would love to discuss this more with you. But
so yes, thank you. We've got your point about the quality factor. Now we move to the grading stage. I do remind all participants that during the clarifying questions, during the replies to the jury questions, really short in time, and we need to stick to the rules because kinda our plan is to run every round within similar timing, to let everyone be in different roles, act in equivalent conditions. So it's not because I'm rude and want to interrupt everyone, but it's just a way how to make our game fair. I hope this long speech was enough to give time jury to give their grades.
Yes, but I'll be open for discussion afterwards.
Nikolai, can you please give us notice when you get all grades?
Of course.
Super.
We are waiting just one jury. Yep, I have received all the jury grades.
Great, thank you. So now we can comment on the round 2, starting with Leandro, if I started with Sonia before, yes. So Leandro, you're first, then okay, then Pierre-Louis, then Sonia.
Yeah, again, very detailed presentation. I didn't like the treatment of errors with more than one significant digit. Some graphs didn't have scale, so it was very hard to understand what was going on. And above all, and this is a criticism for the three teams, you didn't stick to the question that was posed, which is how much information can we get from the spectrum of peas hitting on a container?
Thank you. If you have any comment, okay.
Yes, I do.
Yes, go ahead.
I agree with Leandro that the problem was not completely solved. The problem spoke about both finding the shape and the dimension. The reporter assumed a shape and then deduced the dimension, but I would like to have heard some more general result of the dimension that would have worked for any shape. And as for the reviewer, I think this was a case of a reviewer who was the second opponent, who was already in the presentation pointing out flaws in the reporter, and that is not the job of the reviewer, it is the job of the opponent. The opponent correctly brought up that this did not deduce the shape, and I appreciate that. That's all I can think of.
Thank you. If you move to Pierre-Louis, if you have any remark on the round 2.
Yeah, well, I agree in general with all those that came before me, and really, I'm still not very convinced that. I mean, I saw graphs with different frequencies for your cavity. I found it was very strange. It was pointed out by Ukraine, and I would have loved to see more discussion about this during the review phase. I thought the review phase could have moved in a more productive direction, and for this, the reviewer needs to keep the discussion flowing and avoid getting stuck in some loophole or something. But was nice. Thanks.
Great comments, Hank. Sonia, if you have anything to add.
Very quick comment. So I agree with my colleagues, and okay, I found a little bit flat the position of the reporter with respect to the opponent. He was confirming instead trying to explain, to discuss, and let's say the discussion was not led by the reviewer as it would have been done. Okay, so it's more the comment on the roles they have to play. And then yes, okay, in the reporter there were some units missing. Okay, I don't think missing. I think he said, okay, it's the same unit, but you have to indicate in any case. That's it.
Thank you. Do we need any break? If we need, I can allow only a very short one, like 5 minutes. But earlier we start, earlier we finish. That's great. No one is hungry. Are you ready to start? It's a great preparation.
No. I start when
it's not ready.
Yeah, can you start the timer when I start my speech? Yeah, okay.
Okay.
Okay. Thank you. I have some...
So you're preparing now, right?
Yes. Now we are preparing. When I say good time of day, when you can start the timer.
Okay, thank you. Meanwhile, we can enjoy first slide of Russian.
We can hide this.
I would like to remind everyone who is still alive that after this physics fight, we'll have a short presentation by Bruce Heaney, who will tell us about his path in physics and physics education, and about his amazing experiments, which some of which were a base for IPT problems. So I hope you will still be alive after the last part of this long final fight, and we will see each other soon.
Okay, I can start. Good time of day, dear colleagues. My name is Artem Sukhov. Today I will present to you our solution to the problem number 1, that names cumulative cannon. And the video on the slide clearly shows that we drop the cup with the ball and the liquid from some height and observe the maximum height greater than the initial height. We need to understand how high we can launch the ball with this effect and what is the maximum fraction of total energy we can transfer to the ball. Thus, we dropped the cup and filmed this process on high FPS camera. We tracked the water level in the cup. Until we drop the cup, the water level does not change. When the cup is falling, the height of the water level is increasing. And after the collision, we observe the jet that moves the ball. Let's consider all of these phases. So in the rest phase, the ball moves to the wall due to the asymmetry of the system, because the cup and the ball are wetted and we have some difference in pressure. We have pressure gradient. And the following phase is the main point in our problem. Firstly, we write an expression for the summary force acting on the water. And so the cup falls with an acceleration approximately equal to the gravity acceleration from the experiment, and inertia force plus gravity force equal to 0. Thus, only surface tension and resistance forces acting on the water surface tends to the part of sphere that limited by the contact critical wet angle, and after that, crater is formed. The bottom point of the crater is under the ball, so the jet forms in this point. The jet is formed by collapse of the crater by the ledge breaking accelerations. We call this cumulative jet. Deformations of the cap have little effect on the maximum jet height. We were convinced of this by conducting 2 experiments with the walls lubricated with paraffin and with the rigid walls. There is no effect in the first case, but effect still occurs in the second with rigid walls. So we create the plan of our investigation. Firstly, we investigate the cumulative jet. Next, we describe the energy transfer in the system. And finally, we maximize the height of the ball and the fraction of the energy. We didn't pull all of the important questions into the main report, but we will be happy to observe them. So let's consider the analytical calculation of the jet height. The velocity of the cap and the liquid at the moment of collision we can define from the energy conservation law. At this moment, acceleration acting on the cap, uppercase G, is much greater than the gravity acceleration. We can define work on braking. Suppose all such energy transfer into the collapse of the crater. So we can define the velocity of the water surface. We neglect our drag force and define the jet velocity from the accumulation coefficient, when the maximum jet height is directly proportional to the initial drop height. So accumulation coefficient defines the ratio of the jet velocity to the surface velocity. This coefficient was investigated in book of Vladimir Meyer before us, and this is equation for the cone case. Our crater is a part of sphere, and in this case, we have the equivalent effective cone with the same volume. So we can calculate the coefficient for the part of sphere from the literature. We construct the experimental setup to verify our theory. The phenomenon is badly repeated, and we minimize the human factor in the setup to improve the repeatability of the experiment. And we drop the plane with the cap to save the place of contact with the plane. Separate ways controls the falling plane. We carried out 5 measurements per 1 point of dependence and avoid the parallax effect by the long distance placing of camera. Our model is not applicable at low initial heights because we neglect the dynamic of forming the crater, but we define the depth of crater from the experiments and we drop the cap with the different initial heights and define the depth of the crater before the collision. We can fit this dependence by equation on frame where -4 is coefficient from least square method and Dmax we find from our theory. This coefficient defines the lifting velocity of the water, and surface tension and viscosity of liquid affect the coefficient of lifting. This dependence is increasing as we expected before. We have amended the model by the dynamic of forming the crater, and now the calculation describes the experiment well. As you noticed, we have a numerical calculation. Let me tell you where it defined from. We numerically solve the Navier-Stokes equation with the chosen K-epsilon turbulence model using the ANSYS after-doing program. The numerical calculation by the finite element method was carried out. The mesh was set manually, which slightly worsened the accuracy of the calculation. So we were able to simulate the moment of collision and the process of falling also. We can predict dependencies very precisely with this calculation method. For example, the maximum height of the jet from the volume of liquid. There is saturating column. About boundaries of the model, we will tell you later. Well, consider the transfer of energy from the jet to the ball. We derive the force acting on the ball equation from the energy conservation, change of momentum, and mass conservation laws. We wrote the equation in more detail and solved the differential equation by the Euler method with correction. It is predict and correct the derivative of our equation. We compared and after this we solved this equation. Yeah. We compared the theory and with the experiment and saw the ball accelerates to jet velocity almost instantly. This process you can see on the video. It is our comparison of the model with the real experiment, and we can see that our model described experiment rather well. We can see the same by considering the maximum ball height from the diameter of the cup, and as we can see, dependence becomes saturated, what can be explained by the limited effect on the diameter of the ball by the increasing the jet radius. Finally, we got the maximum height and maximum fraction of energy. Well, consider the boundaries of applicability of our model. There is clear limitation on the sound of speed. Next, there is a breaking point of the cup and the ball. Also, we have limits on the acceleration time, and final limit is air resistance. Limit on the breaking point of the cup plays a key role in our model. So, experimental maximized height is 3.1 meters, and theory calculated these results precisely. It was also important to consider the fraction of the energy transferred to the ball from the jet, which was calculated as the ratio of the initial and final potential energies, and carry out some optimization, which we did from the diameter of the cup. Dependence becomes saturated, and fraction from the fluid volume of the cup. There is an optimum for fluid volume. The biggest ratio that we could get is 23% with a small mass of liquid and a cup. In the end, we thought how to optimize the setup. So we designed the device that names cumulative cannon. We concentrate the jet to hit the ball in the tube. Such a device shoots very high and can well accelerate even large masses. Moreover, we changed the shape of the bottom, and the best concentrating jet was toroidal by experimental. This is an amazing device, isn't it? And thus, we defined the key role of the problem, constructed the launch setup, investigated the main parameters of the liquid and the cup. Also, a rather accurate calculation model is made. We create empirical amendment of greater forming dynamics for the theory. Next, we investigated the mechanism of energy transfer in the system. The theory describes the experiments well. Also, we solve optimization problem for the height and fraction of the energy. In the end, the real cumulative cannon is developed. Bibliography and further research. We can research the strut angle of our cup. Also, we can research focusing effect. It is effect with very small volume. And also, we investigated many parameters like mass of the ball, like radius of the jet, radius from a radius of cup, like vortexes in a cup before the falling our cup, because we can rotate our cup before. Also, we described surface elasticity of collision, and we can answer on your questions about deformations, effect, and decay into droplets. And thank you for your attention. I will be glad to answer on your questions.
Thank you for your report. Now we have time to move to clarifying questions from the opponent team.
Thank you. Could you explain, please, does the result depend on the angle of incidence of the cup? As I see in this video, your cup always fall with the following angle of incidence. Is it true? Did you?
Yes, it is true, and I can answer on this question because we investigate strut angle. We create this const and we create some different cones, and you can see that increases the alpha as right angle, so V decreases the maximum height of the ball.
Angle of cone, angle of incidence, angle of falling.
Angle of cone.
Angle of falling of the glass.
Angle of falling of the glass. If our glass falling with some initial angle, yeah?
Yes, as a key.
Yes, it is a very, very interesting question, and it is important because we create the setup that initial angle of our cup with plane is the same, and it is perpendicular. And if we have some different angles, our theory doesn't work because it is another setup with another geometry, and it is a fact. It is a fact.
Your setup. Thank you.
Okay, may you answer which friction model which you used in your simulation?
Chi epsilon turbulent model, but also we calculated by chi omega model and turbo SST models. We compared the results. Chi epsilon is works on this report.
Okay.
Thank you. Can you please stop here? And now the opponent, you have your time to prepare for your speech. Ukrainian team, if you have any slide, this is time to start sharing them. And we are waiting you on the stage.
You won't take any time out.
Okay, take a time out. Thank you. And your timeout is coming to the end, so we are waiting on the stage with the slides, if any. Your Ukrainian team, we need you on the stage.
Okay, sorry, we have a little problem with the connection. Okay, I'm ready.
Super, start.
Thank you. Good afternoon, dear audience. My name is Oleg Vashtenko, and I'm glad to present you our opposition on the task number 1, cumulative cannon. According to the statement of the problem, the reporter should to investigate how high may a ping pong ball jump using the setup, and what is the maximal fraction of the total kinetic energy of the ball made transferred. Okay, and on the first part of the report, reporter gave us qualitative explanation, and according to his report, he think that the surface tension acting in the system and leads the cumulative jet formation. And also, reporter said that he made the additional experiment with the glass with the paraffin, but we didn't see that experiment, so it is really hard to believe in this qualitative explanation. It's a first. And second, we understand that in this theory, when the glass will fall, the surface of the water will really distort. But in the video, we saw that the initial position in the starting of the collision weren't really distort. So that phenomenon was really clear, explained, but our team cannot really agree with this position. Also, you may carry the additional experiment while you heating the bottom of the glass and obtain the result in this case. So then in theoretical investigation, reporter gave us different theoretical models, and then in the first part of theoretical investigation, he deal with the accumulation coefficient. We think that such a parameter is very complicated to this theory. So there was many different actions and parameters inside this accumulation coefficient. So I think that it's really hard to understand its physical sense. Okay, after that, reporter wrote the Navier-Stokes equation and tries to solve it numerically and simulate the result. Theoretical results were compared with the experimental data, and reporter obtained very good correlation. Really, it's a big question for me, because while you solving as complicated and hard task as the two-phase flow in the Navier-Stokes equation, you may obtain only a blurred picture of this action, but reporter gave us really very precise prediction. We think it's really very strange. Okay, and after that, in experimental investigation, reporter clear provide us experimental setup, but the experimental methodic really should be improved, because we think that using such a device, reporter will not decrease the angle of incidence. He added new angle of incidence, because now there is an angle between the glass and the surface, and new angle between the surface and the floor. And also the part of energy will be involved by the this surface that he threw with the ball, and this is really a big disadvantage, we think. And also nice that reporter investigated main parameters in experimental investigation. So we may conclude that in this task, reporter gave qualitative explanation and demonstrate the effect, but we can't really accept this qualitative explanation. In theoretical investigation, he showed us very precise simulation, and it's really too strange for us. And experimental verification were made on really normal level, but we think that it is possible to improve such an experimental setup. So we propose you to discuss following discussion topics. And first, could you explain, please, what is the cumulative coefficient? What it depending on? What systems parameter define its okay.
Okay, move to the discussion, please. Yeah.
Okay, thank you. But can I, before answer on your questions for discussion, clarify one moment from your opposition? It is about unclear qualitative explanation. I just interesting. What is unclear for you? About
for me, it is very strange when you show your task and say that the main parameter in this problem is a surface tension, and you have not any dependencies on the coefficient of surface tension. You understand me?
No. We have some dependencies like coefficient of lifting, and also we have. I'm sorry. Can I share my the screen because I have only your presentation? Thank you. I'm sharing the screen, and now you can clearly see that we investigated some complicated parameter that is that affect lifting coefficient and crater formatting, and we investigate this parameter, and also we investigate depth of crater, and also investigate this coefficient of lifting, and this coefficient depends on surface tension and also dynamic viscosity. And it is well known that there is no effect in the cup with the balls lubricated with paraffin. It is also information from the literature. It is not only my result, it is a result from the literature that I can show to you in the bibliography. Cumulative effect in simple experiments.
Okay, thank you. Could you please show such an experiment as you say in your report when the ball did not rebound as a result of using paraffin?
Oh, I'm sorry, but I haven't this video. But in this video, I see that water level increases after the collision, but not like the jet. It is like oscillations by the deformations, vibrations. It is a very low effect. It is not concentrate the jet, and there is with the big cumulative cannon that we have only cumulative jet.
Okay, thank you. Next question about this. We can now carry out the additional experiment, mention additional experiment. So imagine that you have the glass and you hit it
like this,
just hit, no falling. Will the ball rebound or not?
Only on the very low height, and we check it if we push this glass between two very I don't know rigid surfaces, and our glass didn't accelerate between these, we haven't any effect.
Okay, thank you
Oh, I'm sorry. Okay.
Next question. From your theoretical from your qualitative explanation, it is clear that there are possible situations when the ball will not involved by the jet. Did you consider these situations?
Not involved by the jet. Can you? I didn't get your question. Can you rephrase?
Okay, when the jet goes on the one side and ball goes on the other side.
Yes, we have these considerations from the experiment before our experimental setup. Because before our experimental setup, we have very different angles of collision, and there is effect from the, I don't know, from the not flat surface of the water.
So you designed this experimental setup to decrease the angle.
To decrease this effect, yes.
But we you obtain the increasing of this angle.
No, it's not. Increasing angle of falling plane and surface, but not increasing angle between cap and falling plane. We have perpendicular angle, perpendicular situation with cap and falling plane.
Appears on the stage of fall. So it appears on the one side of the glass, and then while it hits perpendicularly, it will be go on the one side.
Yeah. It is effect on the height. Thank you.
Thank you, everyone. We need to interrupt the discussion and add the reviewer to it. So please, the team, you have your time for clarifying questions.
All right. So first of all, I would like for both teams, in a few of the videos provided, we saw that sometimes the ball would rest touching the edge of the vessel. So is that important?
May I?
Yes, please.
Thank you. I think that it's really very significantly important part of the report, and I think that reporter should investigate it in his theory. And my question was really related to your question. Thank you.
Yes. For the reporter, do you think that's relevant because you disconsider it? Do you?
I think that it is relevant, but
that's fine for now. We can discuss later.
It is important. Thank you.
Yeah. Okay. So, are the effects of parallax considerable, given that experimental setup?
No, because we place the camera at very long distance. But we have two cameras. In this video from nearby camera, and this video only for moment of collision.
Okay, so we can discuss more about that later, but okay. So now consider that I want to maximize, is a very short question, so just answer with the least amount of words. So consider I want to maximize the energy transference for the same ball and cup. So should I fill it more with water or should I fill it less for both the reporter and the...
I think that for maximizing the part of transferred energy, there is a maximum, and we should find it, and the reporter should find it. Yes, we are really.
But should you feel more? Should you feel more or less with water? You have the same cup. Should you put more water or less water?
Less water.
Important to understand that it's really has a maximum. You shouldn't say that you should. You can say that it's need to use no water or use 100 liters of water. So we have a defined maximum. Yes.
Okay. Yes.
Okay, great. Thank you. We now should move to time for preparation for the reviewer.
I call timeout.
Okay, I got your point about the timeout.
Can I call timeout?
Yes.
Okay.
Okay, US team, we are need you on the stage.
Okay, so one of my teammates will start. Actually, I need you to stop sharing so that I can. Okay, there. All right, so I will start now. So first, I would like to, as we keep going, I would just talk with. Oh, the slides are coming. Okay, so. First, I would like to talk about the reporter. He has a very good explanation of the mechanisms in importing burden in surface tensions and all the forces acting on the ball as it falls, and good qualitative explanation of how it works. It gives a numerical simulation of the two-phase flow Navier-Stokes equation, which is, using finite elements method, which is acceptable. And of course, you take a lot of things into consideration there, although you need to specify a lot of things and a lot of boundary conditions and initial conditions that I haven't seen done, and I would like to see discussed during our discussion. So it tried to minimize some factor, the effect of some random factors in his experiment, like the angle at which the cup hits the ground. That's a good thing. And also very good predictions qualitatively and quantitatively. And actually, that's another point that I think the opponent pointed out, and I would like that more discussed. He has maybe too good of a match between theory and experiments for a low control experiment like this one. So yes, I would like to see that approached during the next fight. So it did not consider the contact between the ball and the wall that we talked. But now let's talk about the opponent. The opponent brought up some good points. We actually agree with them about the fact of the ball touching the edge. We agree with, however, in the other question we made, we agree with the reporter about putting less water would give a more a higher energy transference ratio. But now, again, about the reporter, he pointed out these good things. I pointed out also about the angle, but the angle wasn't the biggest issue, I think, in his experimental setup. I think during the fight, I will brought up what I think was more significant. I would like to see you guys discuss that. I think that the angle you solved, the reporter solved well, but not other factors that we could improve that experimental setup. So the discussion they had could be summarized about how applying paraffin affect the phenomenon, which I think was kind of resolved during the were already clarified. Can the phenomenon be reproduced by hitting non-moving glass, which also I think was pretty clarified. And when the jet position does not coincide with the ball, it was a very good point brought by the Ukrainian team that needs to be discussed. And that is one of the reasons why I'm concerned with such a good match between experiments and theory whenever we see this kind of thing not being considered and they are appearing in the video. So I think we should now proceed to the discussion. So first of all,
go on, yes.
Can you stop sharing your screen, please?
Yes, we will. Okay, so first of all, I would like you guys to discuss about the fact of the ball resting, touching one of the borders of the cup. So yes, please go
like
on.
this, because in the rest phase, our ball averted and moves due to the wall. I'm sure in this fact, but in the process of falling, we have formed some crater, and you can see this by the experiment.
Yes.
And after that, our balls moves in some different position, and we have some another geometry, but our theory predicts this well because we have cumulation coefficient, and this cumulation coefficient we can predict by the geometry, by the contact angle of liquid and the cup.
Yes, that's fine to know. But my main concern, and that I would like the opponent to give his opinion, is whenever it hits the ball, we see in some videos that it goes out of the cup rotating. So please, opponent,
about
could you
rotate?
discuss that?
No, can I answer, please?
Okay.
Yes, please discuss. Yeah.
Yes.
In experiments of reporter, in our experiment too, where we saw that ball really very frequent hits on the wall and move near the wall, and it's you can't really rotate this fact, because firstly, it's true, we didn't saw in the in your report any fact that may
about rotating of the ball, yeah?
Firstly, yes, it's the fact that
I think that it is not very important because we have a very small masses of the ball, of the ball. We have very small masses of the ball. We have very low energy, rotating energy, because we have very low radiuses, and also we have very low angular velocity. I can show to you the video. For example, this you can see that the ball rotates at very small angle, but how this can affect the maximum height? Maybe can explain? Maybe can you explain this, because
as you can, the jet wasn't on the center of the ball.
Yes, it is really true. I'm sure here.
It's the first, and second, the ball will rotate really fast, more faster when it will be on near the wall, and it's first. Yes.
I'm sorry, but it is about one rotating per I don't know per yeah.
I think we should move on now. This discussion, I will have to agree with the opponent in this point. It does affect the.
And also we can add other team members to the discussion now. It's
yes.
time to.
All right. So I would like
everyone.
you guys to discuss, while some people can say in the chat that they wanted to participate, but I would like you guys to discuss one thing that is shown in the video, wasn't mentioned by the reporter, but they do this thing of rotating the liquid in the cup and then adding the ball. How does that affect the phenomenon? Could you guys discuss that? I think that's a very important thing, because it avoids the previous problem we had, and it also has some other effect. Yes, please, if you guys would like to discuss that.
Yes, we investigated this, and also if we can describe the vortex level in the vortex level in the cup, and we have some problems with this, because time of vortex life is much smaller than time of falling, but it is for our height. But for the height about, I know, maybe 10 or 20 centimeters, we have this effect, and this can affect on the initial position of ball and the crater forming. It is about crater.
Maybe we should let the opponent now give his opinion.
Okay, thank you. Now I really agree with the reporter in this case, but I have a really hard question. How the rigidity of the glass affect on this phenomenon? As you can see from your in your video, the glass really perturbates during the experiment, and also in your report that was a fact that and the high when the glass fallen on the high of 2 meters, it will destroy. Maybe use another glass and repeat the investigation of dependence of the height.
But we also have investigation with real cumulative cannon, and this is very rigid body, and there is effect still occurs and occurs very well, as you can see.
Okay, I saw this investigation, but according to the statement of the problem, you should use the glass.
We need to, I'm sorry for interrupting you. We need to maximize our height and also maximum fraction, yeah? And we confirmed that if we have some initial angle, we have low height. Are you sure?
My question was about rigidity properties of the glass. How
properties? Oh, I'm sorry.
Phenomena.
For example, if we have initial strain, initial deformations, we have a low height of the ball, and we also investigated this. Also, we changed the surface, but the surface elasticity, but the surface is neglectable because we have the same height about for different experiments.
Yes. Maybe we could build up on that and ask, how did you model your collision? Because it's probably going to be a boundary condition for your Navier simulation.
Yes.
I think that's very important, and I would like you guys to discuss about it.
About boundary conditions, about deformations pressure. Yeah. Yes, we also have some deformations pressure, but we neglect them in our model. It is real fact. And if we have some big deformations, we can predict them. These experiments also we cannot predict cases when our glass is breaking. It is another experiment for materials. It is not only about our effect with cumulative cannon, but it is effect on the situation. It is real.
Does the opponent want to add anything on that?
Yes, we want to add and to ask about the initial distribution of water in your simulation. Like, we understand that there is a we will get different result depending on the acceleration of the change of the water velocity. Have you investigated it in simulation, and what initial distribution you your simulation?
We considered only the symmetry situation, actual symmetry with actual symmetry crater, like in the ideal theory. Only this.
Okay, and what happens? Like the velocity decreases rapidly, or what in your simulation?
If you need to some interesting results, we have results about very narrow area in investigation. It is, I'm sorry.
Okay, although this is what I mentioned and what is pretty interesting, I think we are out of time. So
yes, I want just, if you show anything in short time, please show. If not, we finish the discussion.
Okay.
Okay, so You can move now to your concluding remark to make a conclusion of overall discussion.
Okay, thank you for the opponent. Also, thank you for the review, because it is very good discussion, and I have many ways to improve my presentations, but my presentation, also my investigation. But I remind to you that we need to set up, create a stuff for very high cumulative, very high maximum height of ping pong ball. Also, we need to maximize fraction of the total kinetic energy that transferred to the ball from the jet, and these points investigated in the report. But also we have many interesting effects, and also we can observe very big cumulative jets with big crater in the big initial radiuses of the jet, and it is well known. Also, we have many another effects. Thank you.
Super. Thank you very much. So now we can move to the last portion of jury questions. And now we're starting, I forgot already who we're starting now. So let's start with OK now.
Okay, my question. I heard the reporter say that surface tension was important. And I wonder then what would happen if we had no surface tension at all?
Okay, it is question for me, yeah? Okay, if we haven't surface tension, crater is not formed in process of falling, but also we have some another interesting effects like waves on the flat surface of the water, and it is effect on very small initial height, and this effect can move the ball on the some high height when the initial, if this is small height. Also, we have some deformations effect and deformations pressure, and it is
But do you think it would go higher or lower?
It is lower than cumulative jet. It is.
Okay. And opponent, would you agree that removing the surface tension would create lower ball height?
We think that effect will be observable, but like we cannot judge about it so easily. Mainly, we agree with the reporters. Yeah.
Okay. Thank you for answering my question.
Okay, now we move to Pierre-Louis. If you have any question, please ask.
Always. A question for all three teams, actually, taking the lead from, okay. If you had no surface tension, but you swirl your glass, you make the vortex on a fluid with no surface tension, what would happen? Would you have the cumulative jet or not?
Yeah, yes, from some initial heights we have cumulative jet because we have some initial vortex, and for this effect we have a crater, and this crater may collapse, and this is possible. But if we have some initial energy, rotation energy of a vortex, we have I don't know. I think that it is some another cumulative jet, not by formatting a crater in the falling process. It is some another, I think, and it is lower than the cumulative jet from the falling process.
Of course, yes, we obtained a very similar result, and the height of the rebound will dependent on the depth of this crater that you will make. But it is very important to understand that this crater may exist in the moment of collision. So in the moment of collision, the surface makes straight and the ball rebounds. So yes, we will obtain very similar result, and even it may be higher than on without any vortexes by only with the surface tension. Yes.
I will agree and add up on the answer of the opponent. I also think that this would also prevent the fact that the ball might lay on the edge of the cup, and because it's of course inside the vortex, so it's not touching the cup, and so that would prevent rotation. It dissipates energy. Instead of you having linear kinetic energy upwards, you are having rotational energy. So actually, I would believe that it will go even higher. Yes, it would work and it will go higher.
Okay, thank you.
Okay, if that's it, we can move to question from Sonia. Sonia, do you have any question?
No question.
No question. Okay, Leandro, do you have any question from your side?
Just a curiosity, with the optimized cannon that you developed, you calculated a height of 10 meters, right? Did you consider other losses? Because when you're talking about 10 meters, maybe air drag effects may become important. I would like you to comment on that.
Yes, it is very important, and we cannot neglect this effect in this case, because it is very big height, it is very big velocities, and we need to calculate the Reynolds number for the motion. We need to investigate what is friction, what is the friction nature, it is turbulent or no, it is viscosity, it is turbulent in this case, I think. And we need to take into account this factor for calculating this height, but it is not for some glasses with plastic glasses like in the video of the problem.
So that value is calculated, it was not measured, right? The 10 meters.
10 meters is estimated by the video, but it is not. It is about very big height, initial height.
Okay, I have another question to the opponent team. You mentioned in the beginning that cumulative effect is not the key. Cumulative is not the key effect. I couldn't understand what you meant by it, because we're talking about cumulative effect.
No, we meant that the surface tension effect is not a main. We said
okay, all right. So my bad. Okay. Yeah, so that's all. Thank you.
Thank you, everyone. Thank you for the discussion. So now our participants are free, and I really want to thank everyone. You did today a great job to run through two complicated fights in this complicated environment. So now we are waiting for grades from jury members. Please send them to Nikolai. And at that point, we're going to have all grades collected. After the fight, after we listen to all comments from jury members, we suggest you to stay in the same room. Just at that point, you stay muted as all other participants who are watching now our YouTube translation. And we're going to listen to Bruce's presentation while we are calculating the final results. And then we're going to announce the results of the entire tournament and greet the finalists and greet the winners and so on and so forth. Nicola, please get us notice when all grades are collected.
Okay.
Meanwhile, we can enjoy Bruce's workshop. It looks gorgeous.
So yes, now I see the marks from Oke. I see the marks from Leandro. I see marks from Sonia, and I see marks from Pierre. Yes. Yes.
Super. So please, let's get comments about the last round and about the entire tournament, starting with Pierre-Louis. Please go ahead.
Oh, thank you. Well, I'd like to congratulate all three teams. I think this was a very nice fight. Team US did a good job in making the discussion flow and going from one topic to the other. Team Ukraine raised very interesting and very relevant topics on a problem that was very well solved by the Russian team. So it wasn't an easy opposition, and you managed to raise some interesting points. So congratulations to all three of you.
Thank you for your comment. Sonia, if you have anything to add, please fire away.
Yes. Okay. The fight was very interesting, and I have to say that okay, I liked the reviewer, and I found that also now the opponent and the reporter became closer to the one I was expecting. So this means that there was an improvement even in between. We were doing the three fights. So, however, as is the last comment, I'm really impressed in the sense that, okay, it will be really hard to say that there is a winner and the others are no winners, because all the teams, they have very good points. So good luck for your future in any case.
Thank you, that's nice, warm words. Leandro, do you have anything else to say? You can also comment specifically on physics, yeah.
My general comments are, I enjoyed very much this last fight. I think the presentation was very good. The problem was well solved and well presented. And what I didn't really enjoy was the opponent and the reviewer kind of focusing in details rather than advancing the main conclusions. I mean, of course, they talked about important points, but in the big scene, I think there were aspects that would work better to make the knowledge advance.
Yeah, super, thank you. And okay, please go ahead with your comment.
I can echo what Sonia said, that I think that the reviewer did a good job in bringing the discussion forward. I was surprised to see such a good review from what I believe is that team's first review. On the solution of the problem, my slight concern is with the simulation that was done. I didn't really understand how the ball entered into the simulation, and I think it's necessary to model the liquid and the ball together. But I only made a minor change of my grid with respect to that.
If I can add, I agree with you in the sense I didn't comment about the physics because, okay, you should invent another setup to discuss further.
Thank you for all comments. Thank you for everyone for joining this meeting. Thank you for everyone in YouTube for joining our live stream. I think we've collected all grades. And now I return the word to Evgeny to say something very important.
Yes, thanks a lot, Anastasia, for chairing this long and important fight. We really enjoyed your chairing, and I hope the teams are very grateful to you for your patience and for your nice instructions. And I hope the participants enjoyed observing the fights. Now it's almost the time for Bruce to step up and show us his toys. But before that, I'll just quickly say that we are putting all the marks into the system, and we will make the announcement of the winners and of all the team rankings after Bruce's presentation. So very, very soon. Stay on for it. And Bruce, the floor is yours.
All right, thank you. All my toys, Eugene, that would take us 2 or 3 days to get through them, I think. But no, first off, I'd like to start by offering my congratulations to everyone that's responsible for I lost my picture. Can you hear me? Am I?
Yeah, we hear you perfectly.
And you can see me? Okay.
Yeah, and we see you.
Okay. Let's try this again. I'd like to start by offering my congratulations to everyone that was responsible for this program. This was the first time that I actually got to view the International Physicists program live, and I must say I really enjoyed it. We can all recognize just how tough a year this was for the participants, and I would applaud you for stepping up to the challenge and showing commitment to your field of study. I feel honored to address this group, particularly since I think all of you probably have more formal instruction in physics than I have, or if you don't at this point, I'm sure you soon will have. But irregardless, I would like to give you a few lessons of what I've learned in my education of younger students. I've been a physical science teacher for 41 years. I've taught middle school. I have taught a few classes at high school and college level. I started in 1977, which is probably longer than most of you have been alive. So yes, I can see the shock on your face. Yes, it has been a long time, but it's I must say that it's been an enjoyable journey. Aside with my teaching, I did start a YouTube channel about 7 years ago. It is named Homemade Science with Bruce Yaney. I'm aware that some, if not all of you, have seen it at one time or another, especially since previous tournaments that two of the objects that I've shown were part of the challenges. In my channel, I've tried to demonstrate labs and activities, things that I thought would be of interest to students and get them challenged and interested in science. When I look back on my career, my love for science actually started when I was a very young age. Growing up, I was always exploring with things. We had a chemistry set where I would mix chemicals together and observe what happens, not always in the order that they had suggested. We had old microscopes that we could take and look at things. But I think my favorite area had to be taking things apart and looking at the mechanics of machines, whether they were broken toys that I tried to fix, or sometimes they were items that we had around the house that I would take apart, not always getting them back together. It still was a learning experience for me. But it taught me an important lesson. At a young age, I learned how to use basic hand tools. And when I started teaching, I was very disappointed to see that it was a effort that was lost. Very few students ever took the opportunity to examine the world around them, especially as I got more into the later years of my teaching. With the advent of the internet and so forth, I found that that was becoming a replacement for what I had hoped would be other ways of learning. But anyway, I'd like to go over a few lessons that I've learned along the way. The first one was first lesson was to encourage others to investigate science for themselves. The idea of getting involved with subject matter is something that's been a very strong point with me. I grew up went to school in the 50s and 60s. I'm sorry, 60s and 70s. I'm not quite that old. But at that time, education was typically teacher instruction with very little hands-on investigation. In fact, I like to refer to it as hands-off investigation. My teaching career started the same way with book learning. We had books that we would pass out and students would read things and we'd discuss it a little bit and then we'd move on to something else. This got to be very frustrating to me. So around my third year of teaching, I decided this simply was not the way for the students to learn. This was not how I wanted to teach. And this was prior to this whole STEM revolution, which started around 2000, 2001, I believe. But anyway, at that time, third or fourth year, I had a paradigm shift in my teaching methods. We looked at theory, but we also started looking at investigation. And I think one of my primary goals was to not only teach students about science, but to instill a love for what they were investigating. And whether it's physics or biology or chemistry, it didn't matter. But I wanted them to understand more about what was going on versus theory and then applying it to life situations. Our school had very little money at that time, so I found that supplies were short. So I started a program of looking at ideas that I wanted to teach and then looking for ways that how we could demonstrate them or have my students test them. Pretty much what this program itself has done with the challenges. You look at the theory, you do experiments, and you combine the two to see where it takes you. Over time, we collected simple hand tools. Students were anxious to explore, to see how things operated. So we always had a plethora of devices around, of broken machines that students could take apart and see how they operated. Students were always willing to bring in things. The AV department and other departments were always willing to share additional tools or devices that they could take a look at. So in doing this change, a remarkable thing happened. The enthusiasm for my class skyrocketed. Discipline problems went way down. We covered more material better. Students became more engaged. And I thought I got pretty good at simplifying ideas to the point where I could build equipment that showed what I wanted. And the idea was that others could look at it and with a little bit of help could easily reproduce them themselves. Okay. Eventually, I did start sharing these ideas with other teachers. I had a science company that sponsored me to go around the country for teacher conferences, and I was sharing ideas. And that was the second important lesson I learned, was that was sharing with others. I found that handing out hard copies was a way of, at that time, of sharing ideas, and it never failed to come back to me. Anytime I shared ideas, there were always ideas shared back with me. The advent of social media was actually the next step in my sharing. The files that I had written as hard copies became digital. From digital, we went to YouTube. And at that point, can you move that over? There we go. Thank you. Throughout this time, as I said, I found sharing was going both ways. And it was last year that I discovered that a couple of my ideas were shared with an event called the International Physicists Tournament. The two ideas that were shared, the one, of course, was very simple. It was two cups that had a rubber band wrapped around them for a few times. And you would pour it back and release it, and off it would go. It would rise into a small loop and then continue on. The second one that I was very proud of was something called a string shooter, and I believe this has had a lot of interest in the last few years. And it looks something like this. I turn it on, and it has an endless loop of string. And the story behind it was actually fairly interesting. It actually started out because I was a coach. I helped coach baseball one year, and one of my favorite toys to play with as I was coaching was the baseball pitching machine. So I decided to see if I could make it on a smaller scale. And my first design, which was much smaller than that, and my idea was that I was going to shoot marbles. Well, the idea worked extremely well. I was shooting marbles, I was shooting hard candy, and it would shoot them actually fast enough that they would go over And if they hit a solid surface, they would actually shatter against the wall, which probably is not such a good idea to do with a room full of students. So the glass was quickly replaced with other things. The next step, another projectile I found that was kind of interesting was shooting the coffee stirrers. And so if I can show this on a little bit closer, I would turn, the two wheels would spin, and I would feed the coffee stirrer in between the two wheels, and it ended up shooting it probably, I don't know, maybe 8 to 10 meters with a good shot. So we started looking around for some other things. At that time, I attended a conference out in St. Louis, and someone had suggested to me to try string. So when I tried string through the two wheels, I found that it once again would shoot. I actually need a straw to feed it in properly, but I found it would shoot that out. And of course, the next step was to take the loop and make it into a loop, which is what we found here, which is what was part of the challenge from last year. Now, the interesting thing was that after the challenge took place last year, I had some other educators contact me and shared that, first of all, that it was shown as part of the challenge, and they had additional questions about it. And up until that time, I had completely misunderstood how the device operated. When I looked at shooting solids through here, they were projected forward, and I simply assumed that the string shooter was doing the same thing with the string. But after the review of the tournament last year, I found that definitely wasn't the case. So we have to look at excuse me, I lost my place here. Keep going. Go back one. Okay, anyway, we were looking at the string shooter, and I think last year it was explained that we have to look at the drag that's occurring. And the thing that struck me the most last year, how I could be so far off, was the experiment where someone took the device and shot the string, enclosed it in a plexiglass container, and then evacuated the air out of it. And we saw that the string simply did not give us the same type of reaction or behavior as it did when it was in air. Now, the funny thing was that I did have some. Well, I never expected that air played such, or that the dragon had played such an important role here. I did have some ideas that actually led me to that point. Now that I realize, now that I look back on it, it became fairly obvious. When I look at the string, I found that as I made a new string, I could get a certain loop, maybe 2 meters would be the best I could do. But as it became worn, I found that it would fly better. And when I examined the string a little bit closer, I don't know if you can you see what is occurring here on the string? You notice the little threads coming out of it. I found that the threads actually helped give it lift with additional drag. And at that point, instead of giving me a loop of 2 meters, I was actually able to get loops that were 3.5 meters, which I still find that amazing that we can actually get it to go that far. So anyway, my third lesson that I learned from teaching was to welcome insight from others, and that was something that I've found quite often happens to me on YouTube. Invariably, I will post something on YouTube, some type of experiment, and as soon as I post it, I will have suggestions. Quite often I'll have corrections on mistakes I've made in the explanation of it, and along with that, I will have communication with others where they'll share additional suggestions for investigations. And for me, it's been a learning experience, just like watching this program today has been a learning experience. Working with middle school students have kept me at a certain level where I don't have the opportunity to look at to delve deeper into the explanations of how things operate. And so that's what's so enjoyable today, is watching you folks take these devices, these problems, into a much deeper level than I ever have the opportunity to do. So anyway, the three things I've learned is first of all, love your subject matter. If you can do that, it no longer becomes work. I've taught for 41 years, and if I could, I would have gone another. I would still be going if I had a little bit better health. Share your information. Communication is an important key that I've learned, and invariably, people will share information with you if you're willing to do the same. Which brings us up to one last thing. Next year, I believe one of the objects I have is already listed as one of the problems for the tournament, which would be this piece right here. I thought maybe I'd end with showing this a little bit. This is called a retraction motor, or solar motor, is listed on YouTube. There have been a few variations of this over the years, but this one is my favorite. Very simply, it's made with cups and garbage bags, and when it's put on a pair of supports on the axle, and we turn on the light, we give it a moment, and we see that it starts to turn. And I'm certainly looking forward to learning quite a bit more about this, the concepts and the behaviors behind this, seeing as this is one of the challenges for next year. So anyway, I want to thank you for allowing me to give my views on education for a few minutes. And once again, I'd like to thank you for allowing me into the program. As I said, it's been a learning experience for me, and I hope to continue in the future looking at more programs and hopefully offering some ideas that might make the challenge. So anyway, I think that's about as far as I want to go here. But thank you for putting up with me for a few minutes, and I'm anxious to hear the final results.
Thanks a lot, Bruce. It was a real honor having you here with us during the whole weekend. You are probably our most passionate follower this weekend because it required a lot of time, and you were here and you were following everything and listening to the fights and making your very, very nice comments. And we appreciated that a lot. And of course, next year we will try to invite you in person for the IPT 2021, especially because of this very nice problem that is now in our list for IPT 2021. And if you guys have not seen this list of new problems, go ahead and check it out on the website of the IPT. Now it's time to announce the results. And let me share my screen. I know that it is very late in some countries, so we're sorry that it took us so long, but we still wanted to follow all the steps of the traditional competition of the IPT, offline IPT. Yeah, I will be going through the presentation right now. I hope you can see it.
Yeah, Evgeny, now maybe we can ask teams to turn on the screens, the
Yeah.
camera.
Yeah, it would be nice, guys, here on Zoom, if you can turn on your cameras so that we see you.
Turn off my mic.
And also don't hesitate to turn on your microphones if you want to applaud someone and to write in the chat, send us your reactions. It's very appreciated. Okay. So do you see my screen?
Yes.
Okay, great. And that's perfect. I hope it will not take too much time. Okay, so let's go ahead. So we will start announcing the winners. No, we'll start announcing the ranking from the last position. So on the 10th place this year is a team from China. They are probably not with us anymore because it's very, very late there, but we were still happy to have them. And we tried to adjust the timing of the fights for them so that they could participate. Thank you for being part of the APT. On the 9th place is the team from Pakistan, and it was a new team and the first time the team from Pakistan participated. Again, it was very important to us, and it was great to see the guys making their first steps in the IPT. And on the 8th place was also a new team from India. Great job, and we really enjoyed watching your presentations and your solutions. I'm sure if you polish them next year, you'll be much higher. On the 7th place is the team from Slovenia. Was also very nice to see your solutions, guys. Was nice to chair one of your fights, and I liked a lot your approach and your the depth of your understanding. So again, good luck for next year. On 6th place is France, and we are used to seeing France a bit higher in the ranking, but 6th place is still a very good result. So thank you for being here, even though the situation was not easy, and managing to show us some nice presentations. On the 5th place is Germany. Germany again showed some very consistent performance and some very nice discussions, good data, nice presentation, and again something to improve for next year. I'm pretty sure they got a lot of comments, a lot of experience, and we will be glad to see them next year. The 4th place goes to Colombia, the team that we all like a lot, and that always brings a lot of joy and great Latin American atmosphere to the tournament. And we are really missing seeing you here, guys, and we hope to see you next year in person. And again, you did great. You showed great performance, great team spirit, and we wish you all the best for next year. It was really a short step from the final. And before I tell you about the finalists. Let me quickly go through the prizes that you will get. Unfortunately, this year we did not really have any sponsors, so we could not prepare a lot of prizes for you, but we still wanted to cheer you up and to let you know that we value your participation in the IPT. So you will receive a gift box from us, from the executive committee. Each team will receive it through the team leader, and then every jury member will receive also a small gift from us, because we value your work, your commitment, and that you committed so much of your time this weekend to help us happen, to make this tournament happen. Without you, it would not be possible. And for the finalists, of course, we want to give you some additional prizes. Again, we did not really have a lot of funds this year, but we thought about digital prizes that would be easy to deliver. So we want to present you with 1 year access to the audiobooks providers that are there in your country. We know about Audible in the US, Litras in Russia, and probably something similar exists in Ukraine. So each of the team will get this, and we will get back to you about the details of how you will get it. Also, don't forget that the tournament is not the last thing on the list. We'll also have conference following the tournament in the next 3 days. The link for the conference is published already on the website, the schedule as well, and there will be many nice presentations where you can discuss in more detail what everyone has done on particular problem, and in a more relaxed environment. And you can check out the schedule as well. And for more prizes, don't miss the opportunity of win our awesome IPT pullovers that we made especially for you, and that we want to give out and send out for the best IPT photo. So share with us some nice IPT photos of you. I also promised some prizes for the followers of our online stream on YouTube, and of course you will also get them. Just don't forget to get in touch with us in the Telegram chat. Now the finalists, what you are waiting for during this whole time, and if you can unmute your microphones and do something like this.
Okay. We are ready.
Okay, you are ready? Then the third place goes to United States. Bravo, guys. Again, a new team, and showing such amazing result in the first from the first time. It was really great to observe your fights, and I guess this is definitely a success. So I congratulate you with this beginning. We hope to see the US team next year showing even nicer presentations, learning from the first IPT experience. I know it is not easy to play when you're playing for the first time, but well done, and our congratulations to you. Now again, a moment of suspense, and the second place goes to Ukraine. This was a very tough fight, a very tough competition. The presentations were really full of information, and both teams, all the teams did great work. So it was hard to judge, but Ukraine got second place, and a bit further was the team from Russia, from the Moscow Institute of Physics and Technology, who took the podium, took the top of the podium, and it's well-deserved. Congratulations, guys. It's we saw the quality of your work. We saw how well you were prepared, and this is a huge step from the previous year, because last year the team from Russia, one of the teams from Russia, especially the team from Moscow Institute of Physics and Technology, was on the last place of the IPT. So congrats with this enormous success and enormous jump. Well done. And yeah, round of applause for you. You are the IPT champion for 2020. Bravo.
Well done, guys.
Yeah, we would like to thank you guys again. If you have any words you can share with us. And I understand that the emotions are quite strong now, so feel free.
We need to say something, yeah?
Come on.
I know this is not easy, but you can share with us something.
Say something.
Sorry.
Okay, so we think it was it was the best tournament we've ever seen. We liked the discussions and all the actions. Also, where we find that the tournament finally was even in Zoom. And so, thank you all of the teams once more. We'll see you again.
Yes, and also we have our team member from Ukraine. It is Spina Dmitro. Can you say something?
Yeah, I want two of our team members also organize a tournament for school children in Moscow. And your level of organization was really great. So like people who try to organize a tournament, we want to clap to you, because it was a really wonderful level. And thank you for atmosphere that you create, and for other teams, for my friends and colleagues from Kharkov. It was very interesting to play with them. Maybe last 10 minutes after the final, I thought that we take second place. So it was because they have a very strong report position, and I was also very pleased to hear USA team members their report and their position. They have a very good atmosphere, and it was very glad to see hear how our team members play with them.
Thank you for your nice words.
Can you? Yeah. So we want to give additional thanks to the Rubicon team from the Russian tournament, especially for Sergei Melikov, Sergei Glebov, and Anastasia Chervinskaya, and for our team leaders, Stefan Sladkov and Lev Melnikovsky.
And additional great thanks to Elena Mikhailовna
Bazanova,
who bring our English to a new level, and our whole presentation were almost impossible without her. So thank you very much also.
Thank you for such nice acknowledgements. If the team from US wants to add something, please feel free.
Oh yes, so I'd just like to thank everyone. It was the first experience with IPT for all of us. The first experience with this kind of competition for most of us. Three of us actually had experience with IYPT before, so we knew a little bit. We know how exciting it is, and how these competitions just get the best of us. And yeah, I think we enjoyed a lot, and we will be. We are very excited for next year.
Also, a question at this joyous moment. So for the scoring, is it better to score lower points or higher points?
Usually it's
the
better to score higher points.
But on this slides,
yeah,
US has 3 more points than Ukraine.
I think this is a mistake. You will see the final ranking. You will see the final ranking on the IPT website.
It's very interesting to know our points. So also
I think this 46 is your points. The one which on the US slide.
So it will be published straight away. You can check it out straight away on social media and on the website. I think Russia is 46, Ukraine is 43, and US is 34.
All right, good to know everything's in order. Thank you.
Thanks for being very attentive. It's important. Okay, guys, I don't know if anyone has any more remarks for us. I know that
I would like to thank you, the organization, however, and the invitation. Thank you very much. I enjoy every time.
Thank you, Sonia.
And I enjoy really to see young people fighting in a fair way. And I see them. I remind myself when I was at that time. So it's wonderful. It's wonderful. Go ahead, guys.
That's true. That's why we're doing all that, so that we can bring this community of inspired people together, inspired students, and to motivate you for new and great achievements.
This is the only way.
Again, thanks for everyone for your participation. I know that Team Ukraine had to leave the university because it was really, really late. And probably that's why they cannot comment anything, but they always make a huge investment into participating in the IPT, and their presentations are a gold standard, and everyone knows that. So thanks again for confirming this quality mark of the Ukrainian Physicists tournament. And on that note, I will finish the 12th International Physicists Tournament. The IPT 2020 is finished. The IPT 2020 champion is Russia. Congrats again, and congrats to everyone for being part of this new and interesting experience for this virtual IPT. It was a pleasure having you here.
Can I give one more comment, because we forget our another helpers, another team leaders. It is Mark Bachkov, and also it is team member of team of previous year.
Alexei
Cherkasov. Yeah.
Cherkasov. Yeah.
Yeah, sure. Acknowledgements and helpers are always important. I don't know any example of successful team without helpers and mentors and professors and teachers who support them. So I'm very glad that you could have such an environment this year. It's an important thing to have, and it's a rare thing to have. So definitely thanks to these people. And thanks to Bruce again for being here with us, and for the jury members to staying so late without any breaks. You're the real heroes as well.
Thank you for inviting me.
Goodbye, and see you next year.
Bye. Goodbye. Thank you for the tournament.
Time to celebrate.
Bye.
Okay.
Do we